to recap, first there was the Big Bang, then there was the dawn of man, and then there was JavaScript. So I was the first person to recognize that JavaScript had good parts. That was the first important discovery of the 21st century. And when I announced my results, they were met with wild skepticism. No way, there could not possibly be any good parts in JavaScript. But it turns out that my results were validated, and in fact, JavaScript has some very good parts.
So this is the most important discovery of the 21st century, and you made this.
Yeah, I did that.
It's done.
So to give you some historical background, at the National Center for Supercomputing Applications at the University of Illinois, Urbana-Champaign, there are a bunch of kids who are developing a client program for the internet. At that time, there were a number of protocols that were being considered for the way that the internet was going to deliver information to people. There was WACE, Archie, Gopher, FTP, Finger, and a few others, and the World Wide Web. And these guys didn't know which of those was going to win, so they wrote a program that worked for all of them. And they called the program Mosaic. And because of the way that they implemented the viewer for the World Wide Web won. And the thing that they did was they came up with something called the image tag, which allowed the web to display images, which is something that the other formats couldn't easily do. And because the web could display images, it could look like what you wanted it to be, even if it wasn't what you wanted it to be, and that was sufficient. And that allowed the web to win, and everything took off from there. A bunch of the people from that project were lured to California, where they became part of a company called Netscape. Netscape made the first commercial web browser called Netscape Navigator, and it was a huge hit. It kind of disrupted everything. And they were then planning what to do for Navigator 2. And they added a bunch of new features, including support for electronic commerce. They also wanted to make it easy for end-user programming. They remembered something that had been on the Macintosh called HyperCard. HyperCard was a simple application creation program based on a simple metaphor of stacks of cards. And it was an event-driven script thing, and it was remarkably easy to use, and they wanted something like that in the web browser. So they gave that job to this guy. This is Brendan Eich, very smart guy. He'd been a kernel hacker at Silicon Graphics. His idea was he would write a scheme interpreter to do this. And he was told, no, don't do scheme. Do a language that people like. Make it look like Java or Visual Basic, something popular. This is for the kids. So he was given 10 days to create a prototype of this new interactive browser. And in those 10 days, he designed and implemented a new programming language, which is an amazing achievement. So from Java, he took syntax. In fact, most of the things that are wrong with JavaScript are things that were inherited from Java. There's a language called Scheme, which is a dialect of Lisp that was developed at MIT. And Scheme has lambdas. That's what Scheme calls its functions. And he took Scheme functions and he put them into his language. And there's a dialect of Smalltalk called Self that was developed first at Xerox PARC and then later at Sun Labs. Self took Smalltalk, which was the first modern classical language, object-oriented language, and made it better, both better performance and more expressive, easier to use, by removing one feature from Smalltalk. It's uncommon where someone makes a new language by removing things from another language. Usually it's adding more stuff. The thing they removed from Smalltalk was classes. By removing classes, they could make it faster, and they could make it much better to program. And so he took that idea and put it into his language, and Netscape called it LiveScript. Now, while that was going on, there was another language that was being developed by a guy at Sun named Jim Gosling. He started with something called GreenTalk. He was then moved into a new company that was developing set-top box applications. There, his language became called Oak. That company failed, so he was brought back into Sun, and they tried to figure out what do we do with this language now. internet was becoming popular, the web had become popular, they wrote a web browser in this language. That browser called Hot Java was wildly successful, at least for a short time. And the language that they wrote it in had its name changed to Java, and it became wildly successful. So much so that Sun was making noise that the Java language was going to be the future of software, that if you design all of your programs to target the Java virtual machine instead of the operating system, we can be liberated from Microsoft. And that was a wildly successful message. And Java shoots up like that. It is the most successful launch of a new programming language in history. It's amazing. At Netscape, they're making similar claims. They're saying if you design your applications to target the web browser, it doesn't matter what operating system we're on, and again, we can be liberated from Microsoft. Now, these two companies realized if we're both going after Microsoft, we'd probably better work together, because if we don't, Microsoft will play us off against each other and we'll both lose. So they form an alliance. And the first thing they agree on is that Netscape adds Java to the web browser. And in exchange for that, Sun will drop their Hot Java browser, which wasn't very complete anyway. So check, that's easy to agree to. Step number 2, Sun says you have to kill LiveScript because that's an embarrassment. We're saying that Java is the last programming language you'll ever need. You can't then also be introducing another new language. You're just making us look bad. So kill it. Netscape refused to kill it for 2 reasons. One is they wanted a language for beginners, and Java ain't that language. You need a lot of specific knowledge about Java just to write Hello World. They wanted something with a much lower barrier to entry. But there's also a practical problem. They wanted to launch the new browser right away. And so the way they put Java in was they had Java talk to LiveScript through an interface called LiveConnect. So LiveScript could talk to the browser, Java could talk to LiveScript through LiveConnect. And if they took LiveScript out, Java wouldn't work. And so in order to get Java in there, they'd have to delay the launching of the new browser, and they didn't want to do that because they were on internet time, and they couldn't afford to wait that long. So their alliance was at an impasse and almost failed when one of the founders of Netscape, maybe as a joke, suggested that they change the name of LiveScript to JavaScript, and that they position it not as a new language, but as a subset of Java, interpreted Java, which was silly because Java was interpreted Java. It was Java's stupid little brother. So they went out and held a press conference in which they lied about the relationship of these two languages. And echoes of that lie still reverberate pretty loudly through the internet. Meanwhile, Microsoft has noticed that there are these two companies in California that are getting ready to destroy Microsoft. And they weren't ready for that yet. So Microsoft had completely missed the web and the internet. They thought the future of telecommunications was going to be fax and cable TV. So they went out, they bought a browser company. It was another spin-off out of Illinois called Spyglass, took their thing, relabeled it as Internet Explorer, and decided we need to get one of these JavaScript things too. So they put a team on reverse engineering the first JavaScript engine. Now, it turns out 10 days is way too short a time to design and implement a programming language. And there are lots of errors, lots of bugs, lots of design defects, lots of blunders. The Microsoft team discovers and carefully documents all of them and replicates them. Now, usually when Microsoft goes to knock something off, they can't help doing their own thing to it. For example, when Bill Gates told them, I want a Macintosh, they built Windows. Okay? He didn't ask for Windows, he asked for Macintosh. Okay? That's how it goes there. But on this case, they got it exactly right. And in fact, they were able to keep the write once, run everywhere promise that Java was failing to keep. And in fact, had they not done that, we wouldn't be talking about this language today, but we'll get to that later. But they couldn't call it JavaScript because Sun had claimed ownership of the JavaScript trademark, even though they had nothing to do with the development of the language, because they claimed to own the word Java. And in fact, they were shaking down coffee companies for daring to have the word Java in their URLs. This is true. So they called it JScript, just as they called their implementation of Java J++, because they couldn't get a license to use the trademark. So now Netscape is alarmed that Microsoft is going to embrace and extend us. We're going to lose control of JavaScript. What are we going to do? We need to make a standard. So they went to W3C and said, W3C, we have developed a programming language for the web. We'd like you to help us make it a standard. Now, it turns out W3C had been waiting for a chance to tell Netscape to go to hell. So they told Netscape to go to hell. So Netscape then went to ISO. Eventually, they end up at the European Computer Manufacturers Association, which is a long way to go for a California software company. But ECMA agrees, yes, we'll help you make a standard. So they convene a committee. Microsoft joins the committee. Microsoft dominates the committee. Basically, the standard is based on Microsoft's notes that they made in reverse engineering the original JavaScript interpreter. And they insist that all of those bugs, all those blunders, all those defects remain in the standard, where they still exist today. So there's a lot that's intentionally wrong, which will never be repaired. Now, when they went to publish, it was, what do we call the standard? They can't call it JavaScript because that's a Sun trademark. So they kick around other titles, WebScript, NetScript. They can't agree, so it's published with the working title, ECMAScript, which is maybe the worst name ever put on a programming language. And confusion still exists today. What's the difference between JavaScript, JScript, and ECMAScript? There are people out there who think that they are three remarkably similar but different languages. No, they're three silly names for one silly language. So JavaScript is a standardized language. The edition that is in most versions of IE is the 3rd edition, which was published in December of 1999. Before that one was finished, work began on a 4th edition, which went on for 10 years and was abandoned. In 2009, a 5th edition was published, which defines two languages, a strict and default. We'll talk more about that dialect this afternoon. And then recently, the 6th edition was published, and which will eventually find its way into browsers. We'll talk more about that on the 3rd day. So where do bad parts come from? I think there are 3 sources. One is legacy. A lot of what happens in any language is repeating mistakes that happened in previous languages. And most of what is wrong in JavaScript is not unique to JavaScript. It's wrong in lots of other languages too. For some reason, it just looks stupider in JavaScript. I don't know why that is the case, but it is clearly the case. Another is good intentions. There were a number of features that were added to the language to make it easier, which failed to make it easier. Things like width, semicolon insertion, type coercion, or implied global variables were all intended to make the language easier for people, but they actually make it much harder, at least for professional programmers. And then haste. 10 days is just way too short a time to design and implement a programming language. Brendan did not intend for his proof of concept to be shipped as a product, but Netscape did that. I think that was inexcusable. And he has suffered for that. It was an unfortunate thing. So for the most part, to give you a comparison, maybe the best designed programming language in history was Smalltalk 80. Xerox PARC spent a decade designing, refining, testing, improving that language. They spent almost as many years as Netscape spent days in designing the language. And I think Xerox got it right, even though the community did not agree. So for the most part, the bad parts can be avoided, which is great. And the problem with the bad parts isn't that they're useless, it's that they're dangerous. So JavaScript is an object-oriented programming language, but what it thinks an object is different than most other object-oriented languages. In JavaScript, an object is simply a dynamic collection of properties. Every property has a key string that is unique within that object, and that key string will be associated with any value. You can get a property from an object by using the dot notation or the bracket notation. They can be used in some cases interchangeably. If the bracket contains an expression which is a string which is the same as a name, then you'll get the same property. That makes it possible to dynamically get at things without use of a reflection API. You can set properties of an object simply by assigning to those properties. You can add new properties or modify old properties simply by assignment. And you can also delete properties from an object using a delete operator, although I very rarely see this used. Generally, once an object is made, it keeps its stuff. One design mistake in JavaScript is that the keys must be values, or must be strings. It would have been better if they could have been any value, but they're not. So you can pass any type into the brackets. JavaScript will turn that into a string. So that means effectively the values have to be strings. We have a very nice object literal notation. JavaScript's object literal notation was the inspiration for the JSON data interchange format, the world's most loved data interchange format. In it, you've got curly braces that identify the object. And then you've got named fields or properties within the object. If you don't have to put quotes around the names if the names are valid identifiers. If they are not identifiers, then you need to put the quotes around them. So most object-oriented programming languages are classical. They're all about making classes where objects are instances of classes and classes inherit from other classes. JavaScript has a much simpler, much more highly evolved design, which is based on prototypes, where objects inherit from objects, and that's it. There are no classes. This was the idea that we got from Self, which was an improvement over Smalltalk. But it's a really controversial idea, and most people who are writing in this language do not understand how this really works, but we're going to talk about it. So working with prototypes is actually very easy. You make an object that you like using any of the techniques available for making an object. You can create new instances that inherit from the object, and then you can customize the new instances by assigning new properties or replacing properties. The classification and taxonomy operations that you have to do in an object system, in a classical system, aren't necessary, which turns out to be a huge win. So if you're working in a classical system, when you start off, you have to classify all the objects. You have to figure out what are all the objects, what are they composed of, how are they related. Then you make a taxonomy in which you figure out what's going to inherit from what's going to implement what. And it's a really complicated hierarchy. And usually you're doing that work at the point of the project, usually the beginning, where you have the least understanding of how the object system's actually going to work, which means it's almost certain that you're going to get it wrong. And you see that in that things don't compose properly. You just can't, they don't work. You find yourself wishing you had multiple inheritance because there's no way to get from here to there. And as you layer in more and more classes on top, you find that that brokenness starts to seep up into all the higher layers. And eventually you reach the point where it's so broken that you have to refactor, which means you have to tear it all apart and put it back together again, which is really dangerous because there's a chance it might not ever go back together again. And all of that is due to the coupling of classes. And if you get rid of the classes, you don't have to do any of that, which is really quite remarkable. So the model that JavaScript provides is sometimes called delegation, where an object can only do what it can do, and if it's asked to do something that it can't do, it will designate another object to do that work on its behalf. This is also called differential inheritance, where each object will only contain the material which distinguishes it from the object that it inherits from. The primitive in JavaScript for making a new object is object.create, where we pass it an object, which unfortunately is called a prototype, and we make a new object that inherits from the old one. The word prototype here is problematic because it's so overloaded. All it means is this is the object that we want to inherit from. So let's diagram this. I'm going to make an object called mother, which will have two properties, A and B, whose values will be 1 and 2. And this is the data structure that is created. So we've got our key value pairs, and we also have an invisible pointer to object.prototype. So whenever you make an object literal, it will ultimately inherit from object.prototype. Then if I make a daughter object, I'll use object.create mother, so I now have a daughter. So I've got an empty daughter object, which inherits from mother. So if I say daughter.b plus 2, originally there's no value here, so we get the inherited value of b. Then we add 2 to it and store it in the daughter. So storing operations will always go into the topmost object, but reading operations can go all the way down the prototype chain. And we can have these chains go as long as you want. Generally, chains in this language tend to be very shallow. We don't get the deep hierarchies that you tend to see in classical languages, but if you want to go deep, you can. Then we can add material to the daughter object, which has no relation to the mother object, so we can add more stuff. So generally the way we'll use this is the mother object will be where we put the methods, and then the instances will inherit those methods. Okay? There's also a form, object.create null, which will make an object that inherits nothing. So you get an object that does not inherit from object.prototype. This is handy if you want to make something which is just a container of stuff, and you don't want to be confused by stuff that you might inherit from object.prototype. So that this will act much more like a hash table. Everything in JavaScript is an object. So numbers, Boolean strings, arrays, dates, regular expressions, and functions, they are all objects. So let's look at numbers. Numbers are objects. It's a much simpler number system than you have in Java, in that we don't have ints and integers. We don't have either of those. We just have numbers. We make numbers with number literals. All of these number literals refer to the same object. There's only one number type in JavaScript, which is actually a very good thing. And there are no integer types, which is something you have to get used to, but it's actually a good thing too. The problem is that the one number type we have is the wrong one. It's based on 64-bit binary floating point from the IEEE 754 standard, which is strangely called double in Java and other languages. Anybody care to know why it's called double? Why they picked such a silly name? It's something that comes from Fortran. Fortran had integer and real, and later they added double precision, which was two reals put together in order to give you more precision. And C took Fortran's double precision and shortened it to double, and everyone else has been using double ever since then. So we don't have ints, and I'm glad we don't have ints because I hate ints. Ints have some really strange properties. For example, we can have two ints which are both greater than 0. We can add them together, and we can get results that are smaller than the original numbers, which is insane and inexcusable. And how can you have any confidence in the correctness and the perfection of your system if it's built on a number type which can do such insanely ridiculous things? So JavaScript does not have this defect in it, which I think is brilliant. So one problem with computer arithmetic in general is that the associative law will not hold. And that's because computer numbers are necessarily finite and real numbers aren't. So in many cases, we're only dealing with approximations. And when the values are approximate, then associativity doesn't hold. Now, if you're just confined to the integer space, JavaScript integers go up to around 9 quadrillion, which is pretty big. And 9 quadrillion is bigger than the national debt, so that That's big, right? That's big. So as long as your integers are smaller than 9 quadrillion, they work out exactly. When the integers get above 9 quadrillion, they don't do the crazy wraparound thing that ints do. They just get fuzzy. So if I take a number above 9 quadrillion and add 1 to it, it's like I added 0 to it, which is not good, but it's much less bad than what ints do. And because computer arithmetic can be approximate, then there are identities that we're used to thinking about which don't hold. So you need to be aware of that and cautious. So the most reported bug for JavaScript is that 0.1 plus 0.2 is not equal to 0.3. And that's because we're trying to represent decimal fractions in binary floating point. And binary floating point cannot accurately represent most of the decimal fractions. It can only approximate them, but it approximates them with infinite repeating bit patterns. But we're not allowed to have infinitely long numbers, and so they truncate, and so they're going to be, every number is going to be slightly wrong, which is only a problem if you're living on a planet that uses the decimal system. But on such a planet, you're counting people's money using this. And people, when you're adding people's money, they have a reasonable expectation you're going to get the right sum. And we're not guaranteed to get the right sum with binary floating point, which is a huge problem. Numbers are objects, and so numbers have methods. You don't have to box them in order to get object behavior. Every number is already an object. Every number inherits from number.prototype. So if we wanted to add new methods to numbers, we can do that by adding them to number.prototype. This is not something that applications should ever do, but it is a useful thing for libraries to do. And in fact, this is how we evolve the language. So we can add new methods to new versions of the standard, and libraries can backfill old browsers and old implementations with the new stuff, as long as the new methods can be implemented in JavaScript. Numbers are first-class objects, which means that a number can be stored in a variable, it can be passed as a parameter, it can be returned from a function, and it can be stored in an object. And because numbers are themselves objects, they can have methods. JavaScript has made the same mistake that Java made in having a separate math object or math container for keeping the higher elementary functions. This was done in Java, anticipating that in the future there might be very low memory configurations and they'd want to be able to remove the math functions. But that didn't happen because Moore's law kept cranking on memory capacity, so that turned out not to have been a good strategy. But it wouldn't have worked anyway because you'd be throwing away essential things like floor. There's no good way to get the integer part of a number if you get rid of the floor function, so it couldn't have worked. There are also some constants stored in the math object as well. So one of the things that we get from the IEEE format is something called NaN, which stands for not a number. It's the result of confusing or erroneous operations. For example, if you try to divide 0 by 0, the result is NaN. NaN is toxic, which means that any arithmetic operation with NaN as an input will have NaN as an output. And despite the fact that NaN stands for not a number, it is a number. If you ask JavaScript, what is the type of NaN? It says number, and it's right. The thing I hate about NaN is that NaN is not equal to anything, including NaN. So NaN equal NaN is false, which bugs the hell out of me. And even worse than that is that NaN not equal NaN is true, which I hate even more. So if you want to find out if something is NaN, there is a global isNaN function. And you can pass NaN to it, and it will return true, which is good. Unfortunately, isNaN also does type coercion. So if you pass it a string like hello world, it'll try to convert the string into a number. The number that hello world turns into is NaN. So hello world is NaN, which is not true. So ever since Fortran, we've been writing statements that look like this. X equals x plus 1, which is mathematical nonsense. So Algol got this right. Algol came up with an assignment operator so this didn't look so ridiculous. And BCPL did the same thing as Algol, which got it right. Unfortunately, Thomson liked this better. And so we reverted back to it, and we have not evolved away from this since. So we're stuck with this. And it looks crazy, right? Because it looks like an equation, but there's no value of x which equals x plus 1, right? So it's, except it turns out, if you're using binary floating point, there's a value called infinity. And if you add 1 to infinity, you get infinity. So this actually is an equation. There's a value of x for which this is true. And not just that, there's another value called number.max value, which is 1 followed by 308 digits. It's a really big number. And if you add 1 to the biggest number that JavaScript knows, you would think that would be infinity, but it isn't. It'll be max value. So it holds. In fact, that is true for every number above 9 quadrillion. So there's a lot of values for which this holds. But not nan. Even though nan plus 1 is nan, nan is not equal to nan. So I hate that, and nan is, I hate that even more. So Booleans, there are exactly 2 Booleans in this language, and they are true and false. So hooray, we got that right. We have strings. Does anybody know why they're called strings? Anyone?
The chains of characters?
Well, it turns out nobody knows.
Okay.
The first place I've been able to find in the literature that refers to a specific data type, which is a sequence of characters, is the Algol 60 report. But there's nothing in that report which explains why they chose the word string. I mean, the first time you encountered it, you must have thought, well, this is strange because it doesn't look like a piece of string in any way. So how'd that happen? I asked John McCarthy, who was on that committee, he was the inventor of Lisp, why did you call it strings? And he said, well, Klana was doing this stuff with strings of symbols. He said, but that didn't really answer the question, because at the time of the Algol 60 report, they would talk about strings. A block was a string of statements. So when did it become specifically a string of characters? And he was really annoyed that I was asking him a question he didn't know the answer to. So that was the end of that conversation. And then he died, and he was the last survivor of the Lisp committee, so we'll never know. Or of the Algol committee. So anyway, we got them, and we call them strings. And I think we call them strings because there may have been some CPU architecture which linked characters together to make stringed sequences of characters. And I think that because what's the operation we do on strings? It's concatenate. But concatenate means to form links. It's an operation in chain making. So you would think if it's strings, it should be tie or maybe slice or wind or something that strings do. So we've got some mixed metaphors going on. And so I'm still searching the literature trying to find out where strings came from, but I haven't found it yet. So anyway, we got them. We got strings. A string is a sequence of 0 or more 16-bit Unicode characters. It's characters in the sense of UCS2, not UTF-16, because there's no awareness of surrogate pairs. At the time that JavaScript and Java were designed, Unicode was going to be a 16-bit character set. It later grew to a 21-bit character set, and JavaScript is not aware of that. There's no separate character type. Characters are represented as strings with a length of 1. Strings are immutable, which is good. Once you make a string, it cannot be changed. It's fixed for all time. You can make new strings by concatenating together bits of old strings, but you cannot change a string once it's made. Similar strings are equal, which is great. Java got that wrong. JavaScript got that right. Hooray for JavaScript. String literals can use single quotes or double quotes with escapement. Both work exactly the same way. No magic quotes or quasi-quotes or anything like that. But there's no reason to have 2 ways to make strings, but we do. So given that, I recommend use double quote for external strings, strings that make sense outside of the program, like URLs and templates and notes to the user, that kind of stuff, and use single quotes for internal strings, like the names of properties and character constants, stuff like that. There's nothing that enforces that, but I think it's a good convention. We can convert a number to a string by using its toString method. I prefer instead to use the global string function, which does the same thing, and will also work better on things that do not have toString methods. We can convert a string into a number by using the global number function or by using the plus prefix operator, which I prefer. We also have a parseInt function that I don't like. ParseInt is something that was borrowed from Java. It will convert a value into a number, but it stops parsing at the first non-digit character. And it won't tell you where it stopped or why it stopped or what was left over. And you usually want to know that because that can be important, but it doesn't give you any clue. There was a big design error in that if the string you were parsing starts with a 0, it assumes that you meant that to be parsed as base 8 octal. And so if you're parsing something like a date or a time, which might have an 08 or an 09, that will be parsed as a 0. Because it sees the 0 goes into base 8, it sees the 8, says you are not an octal digit, so I stop here and get the 0. Yeah. So because of that, I recommend you always include the regex argument, which says base 10, we're on planet Earth, damn it. You know, base 10, 0 to 9. Strings have a length property, which tells you how many 16-bit characters are in the string. Surrogate pairs will be counted as 2 characters in that count. Strings are objects, and so they contain a big mess of methods. I'll let you look them up offline, but there are a lot of them. Many of them are actually very useful. Every string inherits from string.prototype. So if we wanted to add new strings to or new methods to strings, this is the place where we could do that. Again, this is not something applications can do, but this is how we've been growing the language. Array is one of the fundamental data structures. It's a contiguous series of, or span of memory divided into equal size slots where each slot is indexed by number. Very fast, very efficient. JavaScript doesn't have anything like that. Instead, what JavaScript does is, well, the first version of JavaScript forgot to put arrays in. And people figured out that, well, we can just use an object, right? We can use the bracket notation, we can pass numbers, the numbers get turned into strings, and it all kind of works like an array, sort of. And that's still what we do. So there is now an array data type. It inherits from object, and the indices are converted into strings and used to retrieve and store values. The good news is that is extremely efficient for sparse arrays. Unfortunately, we don't do sparse array stuff. We're almost exclusively doing dense array stuff, and it's very inefficient for that. One other advantage it provides is that there's no need to provide a length or a type when creating an array. We can just say empty angle brackets, that's a new array, and then you can add as much stuff as you want to it. You don't have to worry about out of bounds errors because it's not really an array, it's a hash table. So every value is in bounds. Arrays, unlike objects, have a special length property, and that property is always 1 larger than the highest integer subscript, which is not necessarily the same as the number of elements in the array. So we can make an array with an object literal, or with an array literal, using the bracket notation. We can have multiple expressions in there separated by commas. Each of those will provide a value to an element. We can append to an array by assigning to its current length, which is really weird looking, but it works. So in this case, my list.length is 3, so we'll assign to it, and the length will now be turned into 3 plus 1, 4. Arrays come with a more interesting set of methods than objects have. Objects have very little useful stuff coming from object.prototype. This stuff is all stored in array.prototype, much more useful set. We'll look at a couple of these. For example, there's a sort method where we can take an array of numbers, and we can sort it. So anybody see what's going on here? But it's sorting them as strings. So it takes each number, converts it into a string, takes the other one, converts it into a string, compares them, and it does that n log times. It's awful. So fortunately, sort can take a function argument which receives pairs of values, and it returns -1, 0, or 1 based on their relative magnitudes. So you can override this terrible behavior, but it's stupid by default. You can delete an element from an array, but it doesn't do what you expect. So usually you want to use the splice method to close up a hole. So let me demonstrate that. So here we've got an array containing 4 elements, and I want to delete element number 1. That'll leave a hole in it, which is identified as the undefined value. If you try to retrieve a value from an array and it doesn't have that element, it returns the undefined value. So if you want to get rid of that, use the splice method. You say, go to element 1, delete 1 element. Then you'll get an array that's more like what you were expecting. And the way it does that is it deletes element 1, it retrieves element 2, deletes element 2, reinserts it as element 1. It goes to element 3, reads it, deletes it, reinserts it as element 2. It's not fast.
Whoa.
There's a look of horror in the crowd. Okay, so because objects and arrays are made out of the same stuff in this language, it turns out you can use just one of them most of the time, which is a really bad idea because sometimes it matters. And because it sometimes matters, I recommend use the right one. Use objects when the names are arbitrary strings. Use arrays when the names are sequential integers. Don't be confused by the term associative array. In JavaScript, the associative array is called the object. We have a date function which was inspired by Java's date class, which was not Y2K ready when it was introduced in 1995. I don't know if they didn't think the language was going to be around that long, or if they didn't see it coming, or what the deal was. But we survived it, hooray, and it's been fixed. So we got that. We got regular expressions, which were borrowed from Perl 4. This is a regular expression literal that matches regular expression literals. That's what I claim. The thing that I hate about this convention is that if you have a regular expression that's longer than an inch or two, it's really hard to have any confidence that it contains what you think it contains and that it matches and rejects what you think it will match and reject. And I will confess I've written regular expression literals that are several feet long, and I am not proud of that. But the language doesn't make it easy to do because they all have to be scrunched together. You can't even use white space in them to kind of separate the elements so you can see what it's doing. And all smushed together, it's virtually impossible for a human to decipher what that is. Fortunately, there's something on the web called regex. And you give a regular expression literal to regex, and it will give you a railroad diagram of what that regular expression does. So you can see what it does, and you can have a good understanding of how it will behave. I will not write another regular expression without running it through regex. Highly, highly recommend it. Yeah?
If you find yourself writing a regular expression that's too many inches long, can't you just get a smaller screen?
Yeah.
Yeah, thank you for that.
I had to, sorry.
No, you didn't have to. So you're probably wondering, when do the good parts start? I haven't heard any good parts yet. Functions. Functions are the good part, and we'll talk about those in the next hour. So in JavaScript, all values are objects except null and undefined. These are what are sometimes called bottom values. And there's some debate as to whether a language should have any bottom values. There's no debate on the question, should a language have 2 bottom values? The answer is absolutely not. That doesn't make any sense. But we have 2. And They act a lot alike, but they don't act exactly alike, so they're not interchangeable. But some people use them interchangeably, which is a confusion. Confusion causes bugs. I don't like that. So I recommend using only one of them. And the one I choose to use is undefined because that's the one that the language itself uses. But both of them are used to represent values that are not objects. These are the only values in the language that are not objects. So if you try to retrieve a value from one of these, you're not going to get anything. If you try to execute them as functions, they'll throw exceptions. They're just used to indicate the absence or the end of something. So I recommend using undefined. Undefined is, I choose undefined because it is the one that the language itself uses. So if I'm only going to use one, let's use the language as one. So it's the default value for variables and parameters. So if you create a variable but you don't initialize it, it actually gets initialized for you with the undefined value. And if you have a function and you don't pass enough arguments in, the missing parameters will get bound to undefined. It's the value of missing members of objects and arrays. So if you try to retrieve a property or an element and it isn't there, you don't get a runtime warning, you don't get a compile time warning. Instead, you get the undefined value, which is actually a very nice thing because it allows you to reflect on objects without any effort. You just ask, you got one of those, and if you get a value back, then you got something, and if you didn't, then you didn't. One thing to watch out for, though, is that you can store undefined into an object, and then you can read that undefined back, but you can't easily tell, am I getting an undefined that was stored in the object, or I'm getting an undefined because it wasn't stored in the object. They both look the same. That's a confusion. I don't like confusion. There's a type of operator in JavaScript which will return a string identifying what the type of something is. For example, if you pass it an object, it returns the string object, which is great. If you pass it a function, it returns the word function, which is great. If you pass it an array, it returns object, which is, well, not technically wrong because everything is an object, but it's certainly not useful. You'd like it to return array because that's what it is. So, but if you pass it null, it returns object, which is just wrong. There's no excuse for that. It doesn't make it hard to detect if something is null because there's only one null value, so you can ask, are you triple equal to null? That's very effective. The problem is you're trying to figure out, are you an object? Because if you're not an object, there are certain things I don't want to try next. And this test fails for that, which is really, really bad. So we have array.isArray now. It was added to the language in ES5. While it's extremely ugly looking, it does finally allow us to detect if some value is an array or not, which is good. And this is how it is implemented on older browsers. JavaScript is a Boolish language in that every value is truthy or falsy. The falsy values are false, null, undefined, the empty string, the number 0, and nan. All other values are truthy, including the string 0, the string false, all objects, all arrays, even if they're empty, all of those are truthy. I think this was a huge mistake. The purpose of this was to allow if statements to work in a way that's similar to the way C works. C is not a strongly typed language, and so it uses 0 to represent the number 0 and false and null and a few other things. And end of strings, and I'm sure there are lots of others. So you could just, so the condition of an if statement in C is 0 or not 0. And JavaScript wanted to look like that, but it turns out to be a bad idea. We'll see some examples of that tomorrow. JavaScript is a loosely typed language in that any of these types can be stored in any variable or passed as a parameter to any function. The language is not untyped, because as we've seen, we've got a lot of very specific types, but it's loosely typed. And I contend this is a good part. And although that statement is very controversial, the prevailing style in the world is calling for strong typing. And there are really good arguments for strong typing. The argument is that strong typing allows the compiler to find errors very early. And the earlier we can find errors, the more valuable that is. And that is true. And so when I first started working with JavaScript, I was very, very nervous because this is a loosely typed language. Any kind of type can be passed in as any parameter or be stored in any property. How can you have any confidence that anything's ever going to work? Because you've got to be prepared for anything at any time. It was crazy. But what I found in working with the language was that, to my surprise, my testing burden did not go up. I thought I was going to have to be watching for all of these things, and putting in explicit type checks of my own, and I very rarely ever had to do that. In fact, what I found was that the sorts of bugs that a type checker can find, you find instantly anyway. If you're doing even the most trivial level of testing, those things show up right away. That type systems provide no help in finding the bugs that keep you up at night. And that you end up doing a lot less work because in a strongly typed language, you end up spending a lot of time working against the type system. There are things you need to do in order to get your job done, and the type system doesn't want you doing those things. And so you have to figure out ways to get around it. And that's a lot of effort. And anytime you cast, then that means the type system is failing you. And you end up casting way too much. Also, it turns out there's a large class of errors which are caused by the type system. Because the type system is causing you to circumvent it, you end up doing a lot of extra work, and some of that work turns into bugs. And in JavaScript, that tends not to happen. So I find in JavaScript, writing correct programs is not harder than in Java. I think it's actually easier. And you do a lot less work because you're not managing all the types all the time. That's my argument. You might not believe me. And it doesn't matter. If you're writing in JavaScript, get used to it, because that's how it works. So in JavaScript, objects are passed by reference, not by value, which means that objects are not copied. In fact, there's no easy way in JavaScript to make a copy of an object, which seems like a surprising omission, but in practice, I've not found it to be a problem. The triple equal operator compares object references, so it'll give you true only if both operands are the same object. There's no easy test for are two objects very similar, containing the same properties, having the same values. That again seems like a strange omission, but I've not found that to be a problem. JavaScript is syntactically a member of the C family. We've got identifiers which can start with letters or underbars or dollar signs. I recommend not starting or ending your property names with underbars or dollar signs, but they seem to be really popular. Dollar sign was added to the language for the benefit of machines, for macro processors and code generators, things that wanted to be able to create names and be guaranteed they wouldn't conflict with your names, that they could use a dollar sign and that made them safe. Unfortunately, some kids found out that you could have a function called dollar and went crazy with it. So dollar functions are all over the place now. We have both formats for doing comments. I recommend using just the / line format because sometimes we want to use comments for commenting out code, and regular expression literals can contain */ and /*. So weirdness can happen if you're using block comments. We have the same set of operators that you would expect to see in a C-like language. A few of them work a little bit differently that you need to be aware of. One big mistake in the language is that the plus operator does both addition and concatenation. This is a bad habit JavaScript learned from Java. In Java, it's not so bad because it's strongly typed, so you can predict which one it's going to do. JavaScript is loosely typed, so it's not until you go to do the plus that it looks at the operands, and if they're both numbers, it'll add them. Otherwise, it'll convert them both into strings and concatenate them, which is bad. For example, in a web application, you might have a form field when you ask the user to type a number into the field, you then want to take that number out and add it to something, forgetting that the value you take out of a form element is always a string, even though everything around it says it's a number. That's a really big source of confusion, and you don't get an error, you just get extremely bad behavior. So we can use the plus unary operator to convert strings into numbers, and so you'll often want to do that as a defensive thing. If you've got a value and you want to add it, and you're concerned that it might not be a number, you can coerce it to be a number before you do the addition. But if you do that, I recommend putting parens around it, because otherwise you end up with two pluses next to each other, which can look like another problem. We don't have integers formally, so you can divide two integers using the divide operator, but you're not guaranteed to get an integer result. So you need to be prepared for that. And because it's binary floating point, even the floating point result you get might not be the one you would expect. The % operator is the remainder operator, not the modulo operator, which is a shame because I think modulo is the more useful one. The difference is in which sign it uses. We already talked about double equal and the problems with it. I recommend you always use triple equal instead, just because there's so many weirdnesses in it, things that are unexpected. There's a meme on YouTube called WAT, W-A-T. Has anybody seen WAT? Yeah, it's a crack up, right? And mostly it's playing fun with this. You know, they take two things which are wildly different and double equal them and it says true, and they go WAT, and they get a big laugh. So don't use double equal. The logical AND operator works a little differently than it does in Java because the operands do not need to be Booleans. They only need to be Boolish. So if the first operand is truthy, the result is the value of the second operand. Otherwise, it's the result of the first operand. It does do the short circuiting, though, so the second operand will only be evaluated if the first one was falsy. And logical OR works in a similar way. The exclamation point is the logical NOT operator. If the operand is truthy, then the result is false. Otherwise, the result is true. If you have bang, bang twice, it'll turn a Boolish value into a Boolean. We have bitwise operators, but we don't have ints. So the way that works is we'll take the 64-bit binary floating point, turn it into a 32-bit signed integer, do the nasty to it, and then convert it back. So in some languages, you'll see people doing a shift because they think it's going to be faster than a multiply. You shouldn't do that even in those languages, because compilers are smart enough. You know, you should write the thing that you intend so that someone reading the program will know what's supposed to be happening. The compiler will sort out the fastest way to do it. But in this language, definitely, you're not going to get any speed improvement by doing the wrong one. We have the same set of statements that you would expect to see in a C language, again with some differences. We've got labeled break, which is good. So if you've got nested loops and switches and stuff, you can break out of innermost things, which is good. We've got the for statement, which we can use to iterate through arrays, but I don't recommend using that. In ES5, we got the for each method, the map method, where you can have a function called on each element of the array. That eliminates almost all need for the for loops. So I don't use for loops anymore. We have a for in statement, which iterates through all of the names of all the properties of an object. Unfortunately, it also iterates through all of the inherited properties, which is usually your methods. And so your methods get mixed up with your data, and it gets to be a mess. Fortunately, we got in ES5, we got object.keys, which takes an object and returns an array of strings, which is just the enumerable own properties of the object, which are usually the ones you want. So I don't recommend using for in either. We already talked about the problems with the switch statement. One thing about the switch statement, though, JavaScript improved the switch statement in one way, and that is that the switch value does not need to be a number. It can be a string, which can be very nice because you can switch on a greater set of values. And the case values can be expressions. They don't have to be constants. So that can be useful in doing internationalized applications, that you can case against a function which will return the yes value for this language. That could be a nice thing. We have exception handling in this language, which is nice. Before ES3, we didn't, which meant that you had to write programs that never went wrong ever, because there was no way to recover from anything. That was hard. So we've got exceptions now. You can throw literally any value. There's a convention that you throw something that comes from a new constructor, which is the same as creating an object that has a name property and a message property. But in fact, you can throw literally anything. So the way that exceptions are used is very different than in Java. So exception handling is very simple. Because we don't have exception types, there's only one catch block. And it catches everything. And generally, it's going to ignore whatever it caught. It doesn't care what happened. All it knows is, or all it cares about is, that didn't work. So let's try something else. Maybe it'll work instead. So in Java, you tend to see exceptions used to implement a form of computed goto, where you can get very complicated control paths that are dictated by whoever threw the exception. And I think that was probably a big mistake. JavaScript didn't make that particular mistake. So we tend to use exceptions properly, use them only for failures. We'd never do normal control paths using exceptions.
Sorry.
Yeah.
Could you clarify that? I didn't understand that statement.
So in Java, there's a tendency to look at why did this fail, right?
Oh, you have different reasons, different catch exception A, exception B, exception C.
Yeah, exactly. You've got a whole bunch of exception cases, and so you've got who threw the exception deciding how you're going to go through your code. And that usually means that the exceptions are not actually exceptional. They're just alternate control paths, right? And sometimes that's motivated by weakness in the type system, that you've got something that wants to return an int, but something else is going to happen, which is not exceptional. It's just not an int. I'm out of values, and so you'll throw an exception instead. Whereas in JavaScript, because we're loosely typed, you can pass a number, or you can pass undefined, or you can pass a string, or you can pass an object. You can return anything that you need to. And so these things are not exceptions. They're just more modes of normal processing. So your control flows tend to get much simpler. Any other questions? Okay, so that's the end of this hour. So let's take a break, and we'll come back.
I have a quick question from chat. People were asking why you don't use for loops and then instead favor for each.
For each is just much nicer. That once you get used to it, it's more readable. In future versions of the language, it's going to be parallelizable. It's a more modern construct. It's more functional. It's more composable. It's better in every aspect.
What about the fact that you can't leave a for each with a return?
I'm sorry?
The fact that you can't leave a for each, like stop a for each loop.
Well, you can. You can, instead of using for each, use every. And then you can have something return false, and then it stops. So Act 3, function the ultimate. You've been wondering, when are we going to get to the good parts, right? Because everything's been pretty horrible up until now, right? Hasn't this been kind of tragic? So we're going to get to some good parts. And the good parts in JavaScript all wrap around the function. Functions are really powerful bits of stuff. In other languages, you'll have methods, classes, constructors, modules. In JavaScript, all you need is functions. Functions are so powerful, they can do the work of all of those things and more. They're just sort of a universal stuff for building things. We make functions using the function expression, or function literal. It will return a new function object, which could then be invoked. A function expression starts with the word function, It can then take an optional name, which allows you to call the function recursively. It also allows for documenting things like the code and stack traces. You pass it parameters, which are a set of names separated by commas wrapped in parens. And it takes a body, which is a block wrapped in curly braces. A function expression produces an instance of a function object, and every time that expression gets evaluated, you'll get a new function object. Function objects are first class, which means they can be passed as arguments to functions, they can be returned from functions, they may be assigned to variables, and they may be stored in objects and arrays. This is very different than in languages where functions are sort of these static things which just kind of exist before the program starts. In JavaScript, the functions run and add things to the environment as they're compiled. And because functions are objects, they inherit from function.prototype. We use the var statement to declare and initialize variables within functions. You don't specify a type in the var statement. It can accept any type. And variables declared anywhere within a function are visible everywhere within the function. So we don't have block scope with the var statement. We only have function scope. So the var statement does a really weird thing. It gets split into two parts. The declaration part gets hoisted to the top of the function, where the variable gets initialized with undefined. And the initialization part turns into an ordinary assignment statement. So here we've got var myvar equals 0. Var myvar equals undefined gets hoisted to the top of the function. And at the site of the original statement, we get an ordinary assignment statement, which does the initialization. To make things more complicated, JavaScript has a function statement or function declaration, which unfortunately looks exactly like the function expression. It starts with the word function. In this case, the name is mandatory. You can't leave it out. It takes the same parameters and takes the same body. So it looks exactly like the other one. The function statement is a shorthand for a var statement with a function value. So function foo expands into var foo equals function foo. And that further expands, because of hoisting, into var foo equals undefined and foo equals function foo. Both of these now get hoisted to the top of the function. It's because of this second hoisting that the language does not allow you to declare a function inside of an if, because the assignment of the function variable is going to be pulled out of the if and moved to the top. So that's illegal. Now, it turns out most of the JavaScript engines allow you to do it anyway, but because the standard says you can't, they all have different opinions on what it actually means. I don't recommend doing that. So it's really confusing having both function expressions and function statements, which both look exactly the same. So how do you tell them apart? And it depends on where you are. If the first token of a statement is function, then it is a function statement. If the word function occurs anyplace else, it's a function declaration. So we talked this morning about scope, about block scope versus function scope. And block scope is a very common thing. Function scope is a very unusual thing, which is unique to JavaScript's var statement. So, and function scope is sufficient, but function scope looks like block scope, or at least the syntax is the same as block scope languages, and so you get confusion. So in some languages that have block scope, you can do stupid things like this, where you can have two loops, both using the same variable name as their induction variable. And it works because in those languages, each of these will be in a different scope, and so they won't interfere with each other. It's extremely unwise, but legal. In JavaScript, it is also legal, but it's worse than unwise, because there's only one I variable created here. Both loops will be using the same I variable. And so they will interfere with each other really badly, and this loop will never correctly perform.
And that's because everything gets hoisted to the top at...
It's because both var I declarations get hoisted to the top, and there is no check to see if a variable has already been declared. So if there's a second var declaration for the same name, good. That's double good. It should be an error, but it's not. And because it's not an error, you can get into trouble. So because of all of this weirdness, I recommend declare all of your variables at the top of the function, because that's where they're actually being declared. And also declare all of your functions before you call them. All of this hoisting nonsense was created specifically so that you don't have to do that, that you can call a function before it's declared. But that requires that all this hoisting weirdness be going on and that you understand what the hoisting is doing. And I think that's too much to expect of the people reading your program. So instead, I think it's much better to say, declare the function before you call it. That's a much easier thing to understand.
But call, you're using the word call, where I think I would call it defining.
In JavaScript, you can lexically call a function before you declare it. I can say,
Oh, I see what you mean.
I can say foo parent, and then below that I can say function foo.
You don't mean say var some function name and then later on define the function. I see. Never mind. These two statements, there's not this parallel between these two statements that I'm looking for. Functions are variables.
No, functions are values that can be stored in variables.
Okay, if they have a name.
Even anonymous functions can be stored in variables.
Okay.
JavaScript functions have return statements. Return statement stops the execution of the function, returns control to the caller, and can also optionally return a value. The return statement can take an expression, it will evaluate that expression, return its value. Or you can have a return statement that returns nothing. It will actually return the value undefined. Or if the function falls through the bottom, it will return the undefined value. I recommend that you not make function objects in a loop. It can be wasteful because every new function object is created on every iteration, so that could be expensive. And it can also be confusing because the new function closes over the loop's variables, not over their current values. And that confusion can lead to bugs. For example, here we've got a for loop which is going to loop over an array of divs. And it's going to add a click handler to each one, which, when clicked on, will alert the ID of the div. And this code looks very straightforward, but it will fail. And the way it fails is no matter which div you click on, they will all display the same ID. It'll be the last one. And it's because what's being captured by the inner function is the current value of div ID, not the value of div ID at the time that the function was created. So the way to get around that is to not use a for loop at all, use for each, and we'll pass in a function which will receive each div as an argument and will alert correctly. We invoke functions with the parent suffix operator, which will surround 0 or more comma-separated arguments, and each of those arguments will be bound to one of the parameters of the function. If a function is called with too many arguments, the extra arguments are ignored. It is not an error. If an argument is called with too few arguments, the missing values will be the undefined value. If there is no explicit type checking on the arguments, on their types, or on their numbers. So if you really care about that stuff, you need to check it yourself. Generally, you don't have to. It turns out most of the defaults in JavaScript are right, so that if you don't do checking, it'll usually do the right thing anyway. So in addition to any parameters that are formally defined as part of a function, there are also two bonus pseudo parameters that you can also get access to, arguments and this. I don't recommend using either of them, but they're both very popular in the language, so I need to describe them both. We'll start with arguments. When a function is invoked, in addition to its parameters, it also gets a special parameter called arguments, and it contains all of the arguments from the invocation. So everything that got passed in the parens that called the function, every one of those values will be in the arguments array. Now, one problem with the arguments array is it is not really an array, even in the weird way that JavaScript thinks of arrays. It is an array-like object, in that it's an object that has a length property, but it's not a magical length property, and it doesn't inherit any of the useful array methods. So it's a difficult thing to work with. You do get arguments.length, which will be the number of arguments that were actually passed. And there's a weird interaction with the parameters. So if you change arguments sub-0, the first parameter also changes. If you change the second parameter, then argument sub-1 changes. For the people who make JavaScript engines, this is maybe the most hated feature of the language, because they're working really hard to try to make it go fast. And you can't go fast when you have to mess with behavior like that. So let me show you an example of how you could use it. So we've got a simple sum function which will receive some variable number of numbers, and it will add them up and return the total. So we're going to get from arguments.length n, the number of things that we're going to add. We're going to loop through n, and we're going to get each of those arguments and add it to the total. Notice I didn't include any parameters in sum, because I didn't need to. I could have, but it wasn't necessary because I'm getting all the material from arguments. Okay, so now this. This is a really difficult thing to have in any language because it makes the language hard to talk about. It's like pair programming with Abbott and Costello. So bear with me. So the this parameter contains a reference to the object of invocation. This allows a method to know what object it is concerned with. This allows a single function object to service many objects, and it's the key to prototypal inheritance. There are 4 ways to call a function in JavaScript: the function form, method form, constructor form, and apply form. 4 forms. I think in a well-designed language there should be 1 form, but we've got 4. And the way they vary is in what happens to this. So let's start with the method form. In the method form, we say some object dot method name or some object bracket, an expression that evaluates to a method name. When we call a function this way, then this will get bound to this object. And it allows the method that gets called to know which object it's going to be manipulating. In most languages, the binding of this happens fairly late, but nobody does it as late as JavaScript. JavaScript doesn't bind this until the moment of invocation. Then there's the function form, which looks the same except we don't have an object prefix, so we just have some function value, and we call that. In this case, this gets bound to the global object. It's the thing that is the container of all the global variables. And that's a terrible thing because it's leaking way too much capability. It's a security hazard. It's a reliability hazard. This was sort of fixed in ES5 strict mode, but not completely. In ES5 strict mode, this gets bound to undefined. So at least we're not binding it to something dangerous. But sometimes it's not what you want either. That if you have an inner function inside of a method, you want the inner function to help the method do its work. But the inner function doesn't get to see this because the inner function gets called as a function, and so this will be either the global object or undefined. So the workaround is in the outer function in the method, you create a variable called that, assign this to it, and then the inner function gets to see that. Then there's a constructor form. It looks like the function form, except there's a new prefix. And when a function is called with a new prefix, a new object is created and will be bound to this. And if the constructor function does not have an explicit return value, then this will be the return value. And this is used in the pseudo-classical style, which we'll get to in a few minutes. And finally, there is the apply form. In the apply form, you call the apply method of the function object, and you get to specify what the value of this is going to be. In addition, you can also provide either an array of arguments, or you can provide individual arguments separated by commas. So to summarize, there are 4 invocation forms: function, method, constructor, and apply. And they each vary according to what they do with this. And again, I don't recommend using this at all, but that's how most people use the language. And I'll show you an alternative in a few minutes. So you all know about recursion. That's when you have a function that is defined in terms of itself or that can call itself. Really important thing. I don't need to tell you about quicksort. That's one of the important examples of using recursion. JavaScript has recursion, which is good. If you're not familiar with recursive functions, I highly, highly recommend a book called The Little Lisper, which has been revised. It's now called The Little Schemer. It's based on the Scheme language, but it's not really about Scheme. It's about recursive functions. And everything in that book can be written in JavaScript. And this web page will give you the key to doing that translation. Highly, highly recommend it. This is one of those books that can significantly change the way you think in a really good way. There's another book called The Principles of Programming Languages by R.C. Tennant. And one of his principles is the principle of correspondence, in which he talks about how variables are like parameters in some languages. So here we have 2 versions of the factorial function. In one of them, result is a variable, and the other, result is a parameter. Otherwise, these 2 functions do exactly the same thing. And so this demonstrates the similarity of variables and parameters based on how the function is constructed. The interesting thing about the second function is it's using an immediately invocable function expression. So here we have a function declaration or function expression, which is creating a new function object, which we then call immediately, passing in the 1. So in general, we can take any expression and wrap it in a function that will return that expression and call the function immediately, and it does the same thing as the expression. It's just more verbose, but it does the same thing. Now, it turns out this is not true in JavaScript for all values. For example, this and arguments change their meaning when you put them in a different function. So it doesn't work for them. But it works for all other expressions. It doesn't, and it works for statements. You can take any bunch of statements and put them in a function and call it immediately, and it says though you had executed those statements. Except that var, function, break, continue, and return change their meaning when you put them in another function. Otherwise, you can do this transformation. And there are some interesting things that can happen as a result of being able to do this. So this is a feature that you look for in a functional language. I promised you some good parts. We're finally getting to a good part. And this is something that you probably don't have experience with. It's something called closure. It's also called lexical scoping or static scoping. It's a consequence of functions that can nest and functions that are first-class values. And JavaScript has it and is almost completely right in the way it implements them. And it's maybe the best feature ever put into a programming language. The context of an inner function includes the scope of the outer function. And the inner function enjoys that context even after the outer function has returned. Now, I expect that statement made no sense to you at all. And I understand that. So I'm going to have to explain this in steps. So we'll start with the observation that function scope works like block scope. So you're familiar with the idea of block scope. So next year, we'll probably have let statements in most of our systems. And here we've got 2 blocks, one inside of the other. And the inner block can see its variables and the variables of the outer block. The outer block can only see its own variables. So I assume everybody's comfortable with the idea of block scope, right? We've had that since 1960, and it's great. So we can do the same thing with functions. You can think of a function as simply being a block with a little bit of extra mechanism attached to it so that you can invoke it in the future, that you don't have to do it immediately. And the same relationships apply. So we've got the yellow function, which can see A and B, and the green function that can only see A, right? Exactly the same relationship. And we can represent this relationship as sets. So this is the set of variables that the outer function can see, and this is the set of variables that the inner function can see. Nothing surprising here, except that we can describe this relationship in that the set of variables of the inner function encloses the set of the outer function. And that's why we call this closure. And it's kind of too bad that we call it closure, because most people think of closure as meaning something else, like retribution or vengeance. I've been victimized, but I'm getting me some closure. It's going to feel good. It's not that kind of closure, but that's what we're calling it. So we're kind of stuck with that. And it seems like a simple idea, right? Just have nested functions which have what should be an obvious relationship because of the way that scope works. But it took a long, long time for this idea to get developed. So you needed a language that had three things. You needed lexical scoping, you needed nested functions, and functions as first-class values. And pretty early on, we got functions that would have 2 out of 3. But we didn't get a function that had all 3 until Scheme. Scheme was an experiment at MIT, an attempt to understand Carl Hewitt's actor model in the early 70s. The experiment failed in that they never did understand what Carl was talking about, but they did discover this new way of programming, which I think was the most important breakthrough in the history of computing. And like all of the really important, significant breakthroughs, the world took no notice of it whatsoever. In fact, it took 2 generations before we finally figured out that this was a good idea and brought it to the mainstream. But it was always a good idea. And the reason it took so long was because of this problem. So we've got the same thing we had before, where we've got an inner function and an outer function. But this time, the inner function survives the execution of the outer function, because the outer function is returning the inner function. So we will call the green function, it'll allocate A on the stack, it will return a new function and exit. Now we want to call the yellow function that it returned, but the yellow function wants access to A, but A is no longer on the stack. Boom. It took us 20 years, 40 years to figure out what to do about this. Turns out the solution is trivial. Don't use a stack. Allocate all of the activation records on the heap, get a good garbage collector, done. Really, really easy. But it took a long time to figure this out.
Can you repeat that, the solution?
Yeah, don't allocate the activation records on the stack. Allocate them on the heap. Get a good garbage collector. Done. That's it. That is the whole thing. So anyway, this idea is discovered in Scheme. Takes a long time for it to finally get to the mainstream. Anybody happen to know what was the first language to bring this idea to the mainstream was? Anybody? It was JavaScript. JavaScript was the first language to do this. It was followed quickly by Python and Ruby. C# got it. Eventually C++ got it. PHP does it in a really half-assed way, but they got it. Just last year, Java finally got it. Java's having a tough time keeping up with its stupid little brother, but it finally got this. This idea took so long to get to the mainstream that there was an opinion that, well, it's not getting to the mainstream because it's not a good idea. The proof that it's not a good idea is that it hasn't been adopted. But we're now adopting it, and we're adopting it because it turns out it's the solution to a lot of the problems that we're having now, dealing with distributed systems and asynchronicity and the things that we do now, much easier if you've got functions working for you. And this particular pattern, where we have a function that survives another function, a function that returns a function, is an incredibly powerful, important construction. It's amazingly useful, amazingly powerful, and we got it. And we got it first with JavaScript, which is amazing. Demonstrate how this works, because I can talk all day about a function that returns a function, but if we don't actually mess with it, it won't make any sense. So let me start with a very simple example. We're going to make a function called digit name. digit name will take a string or take a number and return a string based on what that number is, and it will do that by returning an element from an array of strings. So you can see this is very trivial, and unfortunately there's a problem with the way I wrote this, and that is I'm using a global variable called names. The problem with that is if there's anything else in my system that also has a global variable called names, we're going to get a conflict. And either my function will fail, or theirs will fail, or maybe we both fail. And that's bad. And there is no way you can test for that, because you can't anticipate all of the code that your code is ever going to have to run with. And this is especially a problem in browsers if you have to run with ads, because ads come with some of the worst code you've ever seen, because they'll pay you to take their crap, right? And you can threaten them and say, we're not going to take your ads unless you clean it up. And they say, okay, we'll give our money to someone else. And you say, oh, just kidding. Yeah, that's how it works. And they use lots of global variables, and eventually you're going to get the call, your stuff stopped working because of some ad, but it's not the ad's fault, it's your fault. So we need to reduce our dependence on global variables. So here is another way that I could write this function. Here I've got the digit name function, and it has a private variable called names, because all variables are private within the function scope. So if there is a global variable called names, no conflict. So that's all really good. The bad part is that every time I call digit name, I'm going to have to construct a new array, put 10 things in it, just so I can take one thing out of it. That's hugely inexpensive, or hugely expensive. Now, an optimizing compiler might observe that names is invariant over invocations, and so might try to optimize that out. But optimizing compilers can take many minutes to do their work. And on the web, we can't take many minutes. We have to start instantly. So the compilers are always going to be really fast, get going quick compilers. So they're not going to do this. So we need to do it. So here's a third way to write this function. Here I've got digit name. I've got a function with the private variable containing the names. But this time, I'm returning a function. And the function I return is going to use the names. And I'm calling the outer function immediately, which means that what I'm going to be storing in digit name is not the outer function, but the return value of the outer function, which happens to be the inner function. And that inner function, because of closure, will continue to have access to the names variable even after the green function has returned. This is the most important idea we're going to talk about over these 3 days. So I want to see everybody, including you at home, nodding like, yeah, okay, I got that. Okay? You didn't get it. So let's do it again. So let's start over. This is the original one. Okay, we've got the global variable. We've got our simple digit name function. Now remember the thing we just talked about with Tennant and his correspondence principle, that we can take any value, wrap it in a function that will return that value, call that function immediately, and it's the same thing. So I can do that in this case. I've got, I'm going to assign to a digit name the result of a function which will return a function that I call immediately. So you can see that this and this do exactly the same thing. This one's just a little bit more code. Okay, is everybody comfortable with that?
Could you show those two?
Yeah, so we're going to assign a value to the variable. We're going to assign the result of calling a function that will return that value and calling the function immediately.
So in this example, is the main benefit of using this that we're preventing polluting the global stack, or what are the benefits?
Well, that's where we're going to get to. We haven't done that yet. So these two are doing exactly the same thing. So we still have the global variable problem. We haven't fixed anything yet. Just getting set up. Now, you're familiar with the idea that we can have local variables. If we declare a variable within a function, it's local to the function. And we've got global variables, which all the functions can see. But we can have, so that's two worlds, right? You can think of it as like the instance world and the static world. It's not exactly like that, but it's kind of like that. We got two levels of visibility. But we can go much finer, because every time we nest a function, we get a new place where we can keep stuff. another place where we can get variables. And each function will determine the visibility and lifetime of the variables that are defined inside of it. And so it's not just local and global. We can now have in-between scopes. And they're just scopes. So I'm going to make one change to this one. I'm going to take this global variable, and I'm going to just move it down one line to be inside of the outer function. Okay? So we've introduced a third place where we can keep stuff, which is now in the scope of the outer function. This is the same result that we had before. Okay? So we've got digit name, which will receive a value, which is a function, which is obtained from a function that we call immediately. And that inner function will continue to have access to the names variable of the outer function. So this is closure. This is the big idea, the key idea in functional programming. And this is the good stuff. This is the good part. We're going to spend a lot of time tomorrow playing with this model. Any questions before we go on to the next one? Yeah.
So you solved the global variable problem by moving it in there, but you said that the solution to this was that basically you move the invocation, move everything onto a heap, right? So now in the heap, are you going to have 3 instances of the names array? If you call alert digit name 3, then 4, then 5?
No. So that's a really good question. So you're familiar with the idea of an activation record in a programming language. So an activation record will contain the return address, contain all the input parameters, and might also contain local arguments or local variables and stuff like that. So in JavaScript or in a functional language like this, the activation or a function object will contain a pointer to the code so it knows what to execute when the function is invoked. And the function object will contain a reference to the activation of the function that created it. Okay. So in this case, this function, the object that's created by that function expression will be linked to the context of the green function that called it, or that created it. So through that activation connection, it will have access to the names variable. Not to the value of the names variable that it was created with, but the actual names variable itself. It will always have access to that, and will continue to have it as long as it survives. If at some point I set digit name to undefined, at that point, all of that stuff can get garbage collected. Okay. But until then, as long as the inner function survives and needs that activation, it will keep it, and the garbage collector will not touch it.
Okay, thank you.
So when we call digit name, we'll be calling this function, which will simply go to the array and return a value. So we can call it with 1, 2, 3, and we're just calling it and returning 3 values. We're not creating any stuff because we're just calling that little function. So let me show you a slightly more complex example. This is the fade function. The fade function is something we might run in a browser, which will pass in the ID of a DOM element, and it will change the colors of that element from yellow to white gradually over a couple seconds. And so here's the fade function. First thing it'll do is it will use document.getElementById to look up the ID and obtain a DOM element. And it'll create a variable called level, and it will set it to 1. It'll create a function called step, and it will then call set timeout, which will call step in 100 milliseconds, and then it returns. So at this point, the fade function has finished. It's returned. It's done. Suddenly, 100 milliseconds later, the step function runs. So the step function will go to its level variable, the actual level variable of the parent function, and turn it into a hex character. It will go to the DOM element and change its background color. It will go to the level variable again If it's less than 15, which it will be because it was 1, we will add 1 to it. We're now changing the value of the variable in the outer function. And we'll call set timeout to do this again. And we'll keep doing it until eventually level gets up to 15, and then we stop. And at that point, the garbage collector can come in and take it all out.
So but you call fade, you would just say fade 75. You don't have to say var x equals fade 75. You just fade 75.
Right, well, we'd probably give it a name.
We'll get garbage collected if we don't give it a name?
Well, no, I mean that the argument to fade will probably, because we're talking to a DOM thing,
I'm sorry,
it'll probably
yeah,
be a string.
they have a name.
Or it could be the string 75.
Yeah, it should be a string.
Yeah, but yeah, so we could do that. So suppose there are 2 DOM elements and we want to fade them both simultaneously. So we call fade A, fade B immediately. Will there be any conflict between them? And the answer is no, because every time we call fade, we get a new DOM variable, we get a new level variable, and a new step function. And they will not interfere with each other. They're all within their own function scopes and will be completely unique. So one of the nice things about this construction is that we get that separation so that we can have lots of complex behavior going on without those behaviors interfering with each other.
Each time you call fade, set timeout passes a new instance of the step function to the DOM. Is that correct? And so the DOM doesn't garbage collect those step functions until after it's invoked the timeout, after it's called that function.
The DOM is only involved in that we're calling, we're looking at the style to change the color. Otherwise, the DOM is not aware that any of
I'm
this
sorry,
is going.
set timeout is
The set timeout doesn't actually belong to JavaScript. It does belong to the browser.
the browser.
Node
Okay.
also has it. Yeah. So each time we call fade, we will make a new step function, and we'll pass that step function many times to set timeout until we finish.
I was just trying to get my head around why step doesn't get garbage collected. It's because the browser.
Right, because the browser is holding it in its timer queue.
Okay, it's timer queue.
And as long as anything in the system is aware of something, it's rooted, and the garbage collector won't touch it.
Okay, thanks.
Yes?
What's the initial value of h when you declare it there?
First time, h will be the string 1.
And then what does the toString 16 do?
16, toString 16 means make a hex character. So this will give us from 1 to f. And then we add them to here. So the final color will be pure white, so it'll be FFF. Let's get into object-oriented programming. What do you say? So when Brendan Eich designed JavaScript, he was very strongly influenced by a paper that he read about the Self project. And the Self project was into prototypes, not into classes, and he thought, wow, that's pretty neat. So he decided to put that in his language, but he didn't fully understand it or have confidence in it, so he came up with something kind of intended to be more classical, thinking that the classical guys would like it better. So this is the original intended model for how you were supposed to use JavaScript. So we're going to make a gizmo. That's our gizmo constructor function. We'll pass in an ID, and we'll create a property of the object that is named ID, which will get that value. And we want our gizmos to inherit a toString method. So the way you do that is you say gizmo.prototype.toString equals function, and that function implements the toString method. And the Java programmers looked at this and said, what the hell is that? I mean, this is awful looking. That, what's this .prototype crap? Why are you leaking your stuff? And nothing's contained in anything, right? You want to have your class have some integrity, like it's wrapped in something, and this has its guts spilled all over the place. This is just really awful. But this is how Brendan thought the language was going to work. So let me diagram this for you so you can see what's actually going on. So this is that code put up on the screen. New gizmo is how we make the instance. So this is the instance of the gizmo. We see the ID property that the constructor put in it. This is the gizmo function, because in this language, functions are objects, so they can also have properties. Every function is born with a prototype property, just in case it's going to be used as a method or as a constructor. And the gizmo.prototype is this object. This is gizmo.prototype. And it contains these fields. This is the toString method that we assigned there. And the system also has the object function. That's the constructor of all objects. And we've already talked about object.prototype. That's the thing that all object literals inherit from. So we can add a constructor link here. The constructor property contains a reference to the constructor. So gizmo.prototype.constructor is gizmo. And similarly, object.prototype.constructor is object. You can go around that loop as many times as you want. But the important thing is the delegation link, the inheritance link. So our instance inherits from gizmo.prototype, and gizmo.prototype inherits from object.prototype. So if I ask my instance for an ID, we find it here, we return the string. If I ask my instance for its toString method, it goes, oh, I don't have one. He's got one, so we return this function as though it were part of this object. And if we ask for its foo property, he doesn't have one, he doesn't have one, he doesn't have one, it's undefined. Okay? So that's how Brendan thought you were going to use this language. And there's some good ideas in here, but it's kind of a mess. But you know, you got some idea about what JavaScript's actually doing now. So the new prefix, if it had been implemented as a method instead of as an operator, this is what it would do. It would create a new object which inherits from the functions.prototype property, and will then call the method, passing in that object, binding it to this, and getting a result. And that result is probably what's going to get returned. And again, this is kind of a mess. But we haven't inherited much yet, so let's re-examine this thinking about inheritance. So if we replace the original prototype object, we can then inherit another object stuff. So that made no sense. So let's look at an example, try to figure this out. So we're going to make a whosit. A whosit is something that will inherit from Gizmo. Okay, so we've got our whosit constructor like before, and we're going to replace whosit.prototype with an instance of Gizmo. And then we'll add an additional method. We're going to add a test method to our new prototype. And the Java guys looked at this and said, what the hell is that? I mean, we thought the other one was bad, but holy cow, that's how you write extends? Are you serious? This is horrible. This is absolutely horrible. So let's diagram it. Let's look at what's actually going on here. So here's our instance of whosit. This is the Gizmo function that we had before in gizmo.prototype. There's our whosit function and whosit.prototype, but we replace whosit.prototype with this new instance of Gizmo. So when we add the delegation links, we've got that inheriting from that, which inherits from that, and that will inherit from object.prototype, but I left that one out. So if we ask our new instance for its ID, we get it there. If we ask for its test method, no, there it is. We'll return that method. If we ask for its toString method, go no, no, there it is. We'll return that one. If we ask for its constructor property, we'll go no, no, yes. except it's a gizmo. Oh, oops. So, which I think is not that bad, because you should never ask anything what it inherits from. You should only be asking, what can you do? You know, we should judge our objects by the character of the contents. So, you know, again, that's how it works. And one source of confusion is that sometimes we consider this to be the prototype link, but this one is also called .prototype. So having two pointers which are designated as the prototype pointer, which are completely different and distinct, is certainly a source of confusion as well. But this is how most of the people who are writing JavaScript are using the language. They are doing this. And they are miserable. They're hating their lives, and they're hating JavaScript, and they're angry and bitter and wishing that their favorite language was doing better because, you know, why have they come to this writing classes in JavaScript? It's just awful. So, yeah, so putting them together, there's awful stuff here. Like, you know, there's just the horrendous ugliness and the lack of soothing syntax. We're not getting enough code reuse. For example, both constructors create an ID property, but they both have to repeat that. You know, that's not code reuse. So there are lots and lots of JavaScript libraries in the world, and most of them recognize that there's something seriously lacking here. And so they'll provide some mechanism for sugarcoating this pseudo-classical system in order to make it a little bit nicer. For example, they might do something like create a function called new constructor. And it will make constructor functions. And I will pass into it the thing that I want to inherit from. So I want to extend object, I want to extend gizmo, and I'll pass in a constructor function, and I'll pass in an object containing the methods that I want the instances to inherit. So, you know, it doesn't look like Java, but at least you can recognize the components, right? And so there's something nicer about this. And the surprising thing about this function is that that's the entire function. So JavaScript is such an amazingly expressive language, such a powerful language, that one little piece of code can radically transform the appearance of the language, which is pretty extraordinary. Not a lot of languages can do that. Do I recommend this approach? No, I don't. Even though this is clearly better than using the language as intended, you're still stuck in this classical paradigm, except you're trying to do classical programming in a language without a type system. And that is really, really hard. That classes provide a lot of brittleness, and without the constant type checking to keep you honest, it's really easy for things to go bad. And in JavaScript, things go bad very quickly all the time. And that's why people who are trying to write in this model in JavaScript are so angry at the language. They're constantly in a sense of rage. I think we can do better than that. And I think the way we do better is by going back to the module pattern. That we can take any bunch of stuff and put it inside of a function and invoke it immediately, and it does the same thing, except that in this space we're not creating global variables. This stuff is not leaking out in creation where it's a danger and a hazard. So we can make stuff using this pattern. For example, I want to make a singleton. I want to make one instance of an object containing two methods, first method and second method, and I want those two methods to share private variables and private functions. In JavaScript, there's no easy way to get privacy, except when you're doing this stuff with module or function modules, because each function has a function scope, which is a really effective container for keeping stuff, that nothing leaks out of function scope ever. There's no force in the universe that can force a function to leak what is held in its scope. And we can take advantage of that. And it's a very nice pattern. So what I'm going to store in singleton is not this outer function, because I'm going to invoke that function immediately, what I'm going to store will be its return value, which is this object containing two methods. And those two methods will close over the private state, and those two methods will share that private state. If one changes one of those private variables, the other, next time he looks at that variable, he will see the change. Before we figured out how to do this stuff with functions in JavaScript, the private variable and private function would have been global variables, and there's no privacy there. And one nice thing about this, compared to a classical language, in a classical language, if you want to make a singleton, you still have to make a class, which is a lot of work just to make one thing. Whereas in JavaScript, none of these are very much work. And there are lots of variations on this pattern. For example, I might have, instead of returning an object, I want to have a global variable which is going to be the container of everything in my application. It's going to be this one object which is the root of everything. And I want to enhance it. I want to add a methodical property to our global object that has these two methods in it which share this private state. And we can do that easily. So we don't have to make a class just to make one of. And again, there are lots and lots of variations on this pattern. It's a very rich pattern. And again, this works because we're invoking the function immediately. But if we don't invoke the function immediately, then we could hold on to that function and make lots of instances. So let's do that. This module pattern is easily transformed into a powerful constructor pattern. So here's the recipe. Step one, we're going to make an object using all of the techniques, any of the techniques available for making objects. We can use an object literal, we can use new, we can use object.create, we can call another of these power constructors. Any way we can get an object, we get an object. Step two, we will define some variables and functions. These will become the private members of our object. Step three, we will augment the object with privileged methods. A privileged method is a publicly available method of an object which closes over the private stuff. And step four, we return the object. So it's a pretty simple recipe. It's way too abstract to make sense out of it, right? So we need to go a little deeper. So let's turn it into a template. So step one, I'm going to make a constructor function. And I'm spelling constructor now with a lowercase c instead of an uppercase c because this form of constructor does not care about the new prefix. If you call this function with a new prefix, it'll run a little bit slower, but it will still do exactly the right thing. So this way, we don't have to worry about people forgetting the new prefix because nothing can go wrong. Then I'm going to recommend passing in a specification object. The way you normally write constructors is you'll just pass in some number of things separated by commas. Some years ago, I designed a constructor that had 10 arguments in it, which was a problem because nobody could remember what order they went in. So it was really hard to use. And then it turned out nobody used the third parameter, but we couldn't take it out, right? Because if we took that argument out, then all of the code would break. And so people had to use the third parameter unnecessarily forever. That was really awful and brittle. So what I would do instead is say pass in an object using an object literal. So by just adding two more characters, we can now have named parameters. I can give each of the parameters a name, so the call is self-documenting, so we can see what's getting passed in. We can have them in any order. If we leave things out, we can have nice defaults. If it turns out some parameters become unnecessary, we simply ignore them. We have lots of power in the way that we can manipulate objects, so I would take advantage of that. Also, if we could get the specification object from a JSON payload. So we might have some store and we want to use the constructor to reconstitute the object. We can do that as well. Or to cause the creation of objects across the network using specifications that get passed over the wire through JSON. Then I'm going to call another constructor to make an object, and I'm going to pass the same specification object to him as well. So it may be that that other constructor will make use of some properties in the specification object that I don't need, but that makes sense to him. And if there's anything we both need, we're sharing it. I used to call this parasitic inheritance, where we're going to call another constructor and we're going to take credit for its work. I was inspired by a wasp that lays its eggs in the bodies of live spiders. So the spider does most of the work of making instances, but the wasp gets all the credit. I was going to do something like that. And then I'll take the result of what the other maker did and put it in a variable called that. I can't put it in something called this because this is a reserved word. Then I can create my member variables. I can create as many member variables as I want. And because they're going to be held in the function scope, they're not visible outside of the object, they're only visible inside the object. I will create my private methods, and my private methods will have access to the specification object, to the member variables, and to the other methods as well. I do not use this in here, don't need this. So the code's going to be a little bit smaller and cleaner. And any of these methods that I need to be public, I simply assign them to the outgoing object. And the last step, I return the object. And that's it. And it's a very flexible pattern. There are lots and lots of variations on this, but this is the basic core idea, that we're taking use of closure in order to provide private state within the object. So let's compare this to the pseudo-classical model. So you remember this. It's just awful with all this stuff hanging around. So this is the same thing now in this functional model. And the code gets a lot cleaner. For one thing, we don't have the .prototype stuff hanging off the end. Everything is nice and neat and contained within here. So the Gizmo constructor, very simple. It's simply returning a new object. Notice the curly braces are on the right, so this is going to work perfectly. Instead of saying this.id equals ID, we simply say ID:ID and we're done. Similarly, then our whosit is going to make a new gizmo, and we're then going to add to that function our test method, or add to that object our test method, and return the object and it's done. So the code got a lot simpler as well. Yeah.
I think about 10 minutes ago you were saying not to use this, or that you didn't recommend it, or you didn't like it.
Yeah, that's the next step.
Okay.
So let's suppose we want to have privacy, which is something that I think is very important to have in object systems, so that we may have a goal where the only way to get access to the ID is through the methods of the object, that we don't want anybody to be able to access ID except through the methods. JavaScript doesn't provide any way of having privacy in the classical model, in the pseudo-classical model, because everything you attach to an object is visible to anybody who gets access to the object. So there's no privacy there. But the functional model, because we have function scope and closure, we do. So let's say we want to hide the ID. So you can only get ID through the toString and test methods. The code actually gets simpler. So instead of saying this.id here, we simply say ID. And we're getting it from we're closing over the variable that got passed in. So it's private. It's completely private. And this code got simpler too. We got this ID, which again, we're getting through closure. And the code got smaller and simpler. Yeah?
Aren't the functions copied, though, then for each instance?
Right. So there is a cost to this model. That in the prototypal model, we're saving memory, because we only have one of each method per instance. In this one, we're going to have lots more function objects being created. And we'll talk more about this on Friday, but it turns out that that's significant only if you've got millions of instances. That memory has become so expansive. You've got gigabytes of RAM in your pocket. Making important architectural decisions based on memory conservation is not a good way to go now. And I would contend that if you are worried about millions of instances, maybe this is not the language you should be using. But for most of what we do, the number of objects that you're going to make is going to be relatively small. And performance-wise, this is going to be great. So we're going to spend a little bit more in construction, but we're going to spend a lot less in execution. So I think it's a win.
That fact that you create an instance of that function for each instance of the object, that's because of closure, right? If
Yeah,
we can't have closure without that.
that's right.
Okay,
Yeah, because of closure, we're willing to pay that cost.
right.
And it's not much of a cost. If you look at what is in a function object, there's basically an object with 2 extra pointers in it. One for the pointer to the code, and one the pointer to the activation of the creating function. There's not much else in there. There'll be a link to the prototype object, which is a waste because we're not going to use that. That's it. So there's not much memory in those things, not a lot of work to initialize them. So it's very lightweight. Anybody else? So this also solves another problem that we have in the language, which is related to this binding. So this is the old whosit, the original pseudo-classical whosit. Suppose we want to take the test function out of the object, which we can do, because you can copy any object reference out of an object and put it in a separate variable, and then call that variable as a function. That call will fail, because when we call test as a function, this will be bound not to the object that it came from, but to something else, either to the global object or undefined, either of which will cause this test to fail. But in the new form, because our methods do not have this in them, we can take those functions, pull them out of the object, and call them independently, and they still work exactly the same way because they don't depend on this. So no matter how those methods are called, they will always work correctly. All the fragileness of this is completely avoided.
Just so I'm clear on this, in the middle one there, in your function where you're taking the test ID, you have access to ID because it was pushed onto the heap and it hasn't been garbage collected yet because it's rooted somewhere.
Right.
Okay.
Yeah, in fact, it's being rooted by that object, or
Yeah.
by that method. As long as that method survives, the context it needs will also survive.
Okay.
Episode 4, The Metamorphosis of Ajax. All the world's a page, and all the men and women merely pointers and clickers. So we're going to start this hour with Sir John Harington, a poet, courtier, the saucy godson of Queen Elizabeth I of England. He is best remembered today as being an inventor. And he invented one of the fundamental inventions which makes civilization at our scale possible. Without his breakthrough, we could not live in cities, we could not be living in the density necessary for technological achievement. Great move forward. So this is a picture from his book of his invention. Can anybody identify it? It is a flush toilet, indeed. Civilization couldn't work without them. The Romans had flush technology, but it was lost when the empire collapsed. But Harington rediscovered it, and he built one of these devices for the Queen and installed it in her residence. And as usually happens with the really important inventions, she refused to use it. She complained that it made too much noise. She didn't want everybody in the castle knowing when she was going about her royal business. So it never got used. But he published a book about it, and eventually other inventors saw it and improved it. Over the next couple hundred years, people added other essential elements to it, including the float valve and the S-trap and the siphon, and eventually we
Got
got...
rid of the fish, though. I want fish in my toilet.
Of course you do.
Yeah.
So he wrote a book, and the title of the book was The Metamorphosis of Ajax, which he published in 1596. He called it the Ajax. We'll now flash forward a little bit. This is Jesse James Garrett. He was a designer and consultant in San Francisco. He was on a project where he was consulting with the engineers of a company, and they told him that they had found this way of writing applications for the browser. That instead of doing a page replacement each time the user clicks, instead they will send a little bit of data from the browser to the server. The server will then send a small response back. JavaScript in the browser will then display it on the screen so that they can get much better user experiences using this technique. And it worked. The problem they were having was they couldn't convince their own management that this was an acceptable thing to do. So they asked Garrett if he could please explain to management that this was a good idea. So Garrett goes off and thinks about this problem and thinks about how do we present this idea. And he says the solution came to him when he was in the shower. I think it would have been a better story if he had been on the throne going about his royal business, but he says he was in the shower when it occurred to him that he had to give it a name. And the name he gave it was Asynchronous JavaScript and XML, or Ajax. And he published a memo about this on his company's website in 2005, and it went viral. Almost overnight, everybody was talking about Ajax and writing Ajax applications for the web, and it completely transformed the way we think about browsers and JavaScript. So to give some historical context for this, the web comes from word processing. And word processing historically comes in two very distinct schools. There's the binary proprietary school, which started with standalone equipment and then shared logic and eventually personal computers, which was dominated at various times by companies like IBM, Wang, and today Microsoft. Then there's the textual open school, in which everything is represented as text all the time. One of the first examples of this is a program called Runoff that was developed by MIT. And Runoff was intended for producing text that could be sent to various printers. So here we've got an example of a Runoff file. If a line starts with a period in column 1, that means it's a command. So in this case, we'll skip one line, and then we'll tab 4, we'll offset 4, and so on. And then the text between the commands will be filled into the margins. And this was a very popular program. It was ported from one mainframe to another. It moved all over the place. Eventually it got to Bell Labs, where its name was shortened to ROF. And other versions of it were created, including NROF and TROF. TROF was the way the Unix community did typesetting, made books for a long, long time. Meanwhile, there's an attorney at IBM named Charles Goldfarb who thinks he can do this stuff better. So he begins a project called Generalized Markup Language. And this is an example of a generalized markup language kind of midpoint through its evolution. The markup's gotten a little bit more complicated. Now he's got a colon in column 1, followed by a cryptic command, and then if the command is followed by a dot, he can then have content on the remainder of the line. So he's starting to mix up the commands and the content. And if you're familiar with HTML, some of these commands might be eerily familiar to you, and that's not accidental. And in fact, HTML comes out of this heritage. All of them except for EOL, but you can probably guess what that one means. And in fact, as HTML went through its evolution, we got :E and then : and then finally angle brackets. And so, and you know what happened after that. So if you ever looked at HTML entities, where you've got an ampersand and a cryptic code and a semicolon, and wonder in what bizarro universe does it make sense to have a piece of random punctuation and then a code and another random piece of punctuation? Where did that come from? This is where it came from. He ran out of angle brackets. There was no other way to make it look nice, so he went with the awful looking thing. So where did the angle brackets come from? The angle brackets were inspired by Scribe. Brian Reed was an amazingly bright guy at Carnegie Mellon who made Scribe, which he called a document compiler. This is the first time someone got the separation between content and formatting right. Scribe was a brilliant piece of work. Scribe could take documents and put them to all sorts of output devices. And it had an extremely nice language. That there was one reserved character, which was the @ sign. You'd say @ and then the name of an environment, and then you'd have some quoted stuff which would be affected by that environment. And he had 6 sets of quoting characters, so you could pick the one that's guaranteed not to interfere with the content that you're putting inside. And you could nest these things as deeply as you wanted, and if the nesting got too deep, he had special forms with begin and end so that you didn't care about things accidentally matching. So for long things like chapters and sections, you could enclose them like that. And Goldfarb looked at this and went, oh, angle brackets. I didn't know you could do angle brackets. That's great. So he stole some ideas from this. Unfortunately, he didn't steal enough ideas. So one of the things that Scribe could do was bibliographies. Since it was developed in a university, it has to be able to deal with academic papers and such. So here we've got a description of a tech report and a book. And I believe that this is the very first time that a document format was being used as a representation for data. Because it looks like JSON, right? It's key value pair separated by commas, and it's really reasonable looking. I mean, even things like the details, like year equals 1972, there are no quotes around the year because requiring quotes around numbers would be insane, right? It's just really good. So the GML community got the idea of attributes from this, but they didn't copy enough of the good stuff. And it's a shame that Tim Berners-Lee hadn't been more knowledgeable about text processing systems, because if he had based the web on Scribe instead of on SGML, our lives today would be so much better. But he didn't do that. So, we can see that runoff inspires GML and Scribe helps inspire SGML, but not enough, and eventually that leads to HTML. HTML was not state-of-the-art when it was introduced in the late 20th century. It was intended for simple document viewers. It was not intended to be an application delivery platform. We insisted on using it as an application delivery platform because we needed one, and that was the best thing available, so we used it. But it was not well suited to what we wanted to do. A lot of people looked at it in the beginning and thought it didn't have what it takes, and they were right, but we went ahead and did it anyway. So since then, the web standards were grown from a naive hypertext system under intense, highly unstable competitive pressure as Netscape and Microsoft attempted to destroy each other by manipulating web standards. And it wasn't designed to do all of this Ajax stuff. Its success is due to a lot of very clever people who found ways to make it work despite its design limitations. Now, HTML was a huge improvement over SGML, primarily in that it was much simpler. Anytime you take something that's too complex and turn it into something that's simple, you generally are making it better. Unfortunately, they also made it more resilient. One of the rules in SGML was if you don't recognize a tag, then total failure, nothing happens. And they thought that was too much for the web. So instead, on the web, the rule is if you see a tag and you don't recognize it, ignore it and keep parsing, and it works. And that's actually been good for the web because it meant that we could upgrade. We could have forward and backward compatibility because the browsers would be ignoring the differences as they enter and leave the standards. Unfortunately, the dark side of that is that there were, maybe still are, incompetent webmasters who could not correctly write HTML, and the browsers would do heroic stuff to try to make sense out of the stuff that they were writing, which turned into security exploits, which we'll talk about on the third day. So in the original formation of HTML, authors had virtually no control over presentation. And the thing didn't anticipate applications beyond simple document retrieval, which is a very small part of what we're doing now. It's not internally self-consistent. For example, it provides 2 ways of writing outlines. One is nested, one is not. It's not consistent. And the thing that we call a web page is not a page. It's a scroll. I'm hoping someday we invent pages, because pages are great. Pages were a big step forward in the march of civilization. Maybe someday the web will catch up to that. So the SGML community hated HTML. They thought it was an abomination. They did not like the way it was simplified, and even more than that, they did not like the way it was so much more popular than SGML. So eventually they took over W3C and started changing things to be more to their liking. For example, they changed the way P worked. P had originally been a separator. They turned it into a container. They started the thing about semantic markup, which turned out to be a colossal waste of time. And they also created the XML fiasco. The idea was that they would create XML, which would be the successor of SGML, which would be used as the new document format replacing HTML and be used as the world's data interchange format. It failed at both of those things. HTML, it turned out, refused to die, and it is still the web's document format. And the world's data interchange format is JSON.
Are you said you're going to talk about mythical semantic?
No, I am not going to be talking about semantic markup.
Okay.
You'll have to find someone else to tell you about that.
No, I'm curious as to why you hate it.
It didn't pay off. We spent a lot of time on it and didn't get anything for it.
Yeah, the only folks that we run into that like it are people who have disabilities who want the semantic markup to provide some extra bit of information for them.
I have a lot of sympathy for people with disabilities who are trying to use the web. I don't think that was the solution. But I can understand being desperate enough that, compared to what the web delivers, that anything else might look to be better than what you got. I could talk about CSS, but I just start ranting, and you don't need to hear me rant, do you? Anyway, it's just so it's talking to someone who's finally gotten good at CSS. I mean, it's hard. I mean, the step up to CSS is really hard and difficult. Eventually, designers get there, and once they've done it, this Stockholm thing seems to happen to them. It's kind of like watching a domestic dispute on cops. CSS isn't bad. You just don't understand it like I do. Yeah. Anyway, if all there was to the web was HTML and CSS, it would have been replaced by now. The web would be gone, and we would be working on something else. And this is the proof of that. George Colony, the chairman and CEO of Forrester Research, was saying, another software technology will come along and kill off the web, just as it killed News Gopher et al., and that judgment day will arrive very soon in the next 2 to 3 years. So he was predicting in 2000 that by 2003, the web would be dead, replaced by what he called the X-Internet, which was the executable internet. It was an application delivery system, that he thought that the web was deficient because all it could do was dispense documents, and that is not what the world needed. This quote is no longer on the Forrester website. Archive.org has it, though. You can go to archive.org, and it's right there. So a lot of people heard this message. A lot of people believed it, including Microsoft. So when Netscape self-destructed, Microsoft said, good, we didn't want the web in the first place. So they disbanded the IE team and put them to work on the X-Internet. So they started up the .NET project. They put people on Avalon. They got moving on that stuff. So the surprise was that the web didn't die. And the reason it didn't die was because of JavaScript. That what Colony was arguing for correctly was that the world needed an application delivery system. The thing he didn't recognize was that the web already was one because JavaScript was in all the browsers. Now, the Java community remembers this differently. The Java community is really angry at JavaScript for being in the browser and thinks it's completely unfair that JavaScript was the language in the browser. Had Java been in the browser, things would have been different. Except that's not the way it was. Java was the first language in the browser, and Java applets failed. Java applets were the biggest failure in the history of software. A total, out there in public, huge scale, flat on your face, biggest failure we've ever seen in software was Java applets. They were supposed to write once, run everywhere, and do everything, and they didn't. Total failure. On the other hand, the browser is still in existence because JavaScript was there to save it. So a lot of people who use, or everybody hates JavaScript. There are people who don't know JavaScript who hate it because they should know it. The people who do use JavaScript and hate it actually hate the DOM. The DOM is the API that the browser presents to JavaScript, and it is one of the worst APIs ever invented. It's just really awful. It was designed also by Brendan Eich. He designed it the same week that he designed JavaScript.
Busy week.
It was a busy week. He was handed Danny Goodman's HyperCard Bible, which is a book that's 2 or 3 inches thick about HyperCard. He had never used HyperCard, never used a scripting system. Very smart guy, very quick study. He read the book very quickly and thought he got the sense of it. You know, how do you apply the HyperCard model to the browser? And he came up with the DOM. And it's just awful. It's just awful. There have been many other people over the years who have improved it. For example, one of the most important contributions was Scott Isaacs of Microsoft. He was on the IE4 team, and he looked at the very peculiar model that Netscape had come up with and normalized it in a really good way. In the original Netscape model, not all elements were scriptable, and those that were scriptable were only scriptable in a way that matched what was in the HyperCard book. And Isaac said, let's make them all work the same way, which made DOM programming significantly easier. But they never finished. The reason they never finished was because Forrester said it's done, so they said okay, and they were all put on other projects, and after IE6 it was just left, and that was the end of the story. So they knew it wasn't finished. They never intended to leave it at that state. It's just the web was done, so they went off and did other things. So as a result, it's this incomplete API that's at the wrong level of abstraction that's just horrible to use. So this is a flowchart of a browser. This is how the original web browser worked. You can think of it as a snake. You put URLs on one side, you get pixels out the other side. So you feed it with a URL, that goes to the fetch engine, which will then go out on the internet and find the thing and bring it back and put it in the cache. Then it gets given to the parse engine, which will parse it and turn it into a tree being the data structure which represents the document. The tree is then given to the flow or layout engine, which will figure out all of the components on the page, how big they are, and how they're all located relative to each other, and create a display list. And then the display list gets given to the paint engine, which will then turn it all into pixels, which you can then send to the screen or to the printer. And that's all browsers still do essentially that. When work started on the Mosaic browser, they added the image tag. So this is the hack that they came up with for making the image tag work. When they got to the parse engine and they get an image tag, they'd stop, sneak back to the fetch engine, say, go get that picture, and they'd wait for it to come back, and then they'd resume parsing. They were on one of the world's fastest university networks, so that was working really well for them. But Mosaic got loose, got into the world, and at that time, we were still on dial-up modems. Anybody remember dial-up modems? Can anybody sing the dial-up modem song? Yeah. And so the experience of running Mosaic on those modems was that you would wait until every image got loaded, and then everything would display. So it could take a long time to get a web page going. So when those kids then moved to Netscape, Their goal is to kill Mosaic. They want to create a monster that kills Mosaic, so they make a Mozilla. And Mozilla works a little differently. So when the parse engine gets to an image tag, it goes to the fetch engine and says, go get it, but they then resume parsing. They put a placeholder in the tree to represent the picture, and they continue to parse. And if they see another image tag, they tell the fetch engine, get that one too. They put a second placeholder in the tree, and they continue parsing. And then at the end, they will display what they've got so far. And so you would see little placeholders in the thing, but you saw text right away. And then as the fetch engine delivers the images, they then repeat the flow and the paint to incorporate the new things. And so there'd be an animation effect where it go boom, 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 as the images would appear. So overall, this could take longer than it did on Mosaic, but the user experience was much better because they would see things immediately. And so it was a hit. It was very successful. And all browsers today are essentially doing that. It's just our networks are going so fast that we don't see the placeholders anymore. So in Netscape Navigator 2, they added scripting. So there's now an event loop in the browser, which looks something like this. We'll do the layout, we'll do the painting, we'll then wait for an event, which could be something happening with the UI, someone moving a mouse or typing on a keyboard, or it could be something coming from the fetch engine, something happened on the network, or it could be a timer queue saying some time has elapsed and something happens. Whatever it is, it will cause some script to run. And that script will run to completion. It's guaranteed it will not be interrupted by the next event, which is a good thing, because it makes the scripts much easier to write. That script will probably mutate the tree in some way, that the event probably caused something to want to be displayed or modified, which means we'll then do another flow, another paint, and then we'll get the next event and so on. And that's basically what browsers do. Now this is way oversimplified. There are some mutations of the tree which will cause flow to happen immediately, so it's not in these very clean phases necessarily, but this is pretty much how they work. This is the way of the browser. They all do that. Brendan invented the script tag because he had the problem, where do you put the scripts that go on the page? And since HTML was a text format, he decided to deliver the programs to the browser in text form, which is unusual because most languages will deliver an executable to the execution site. JavaScript delivers source to the execution site. It was because of this problem. So one of the very first things they found when they started writing pages to take advantage of JavaScript was that when you display those pages on Navigator 1 and on Mosaic, the script would show up as text. That was because of the HTML rule. If you see a tag and you don't recognize it, just keep going. And that was hugely embarrassing. And there was no way they could go back in time and tell those older browsers not to do that. So they came up with this terrible hack. They wrap the script in HTML comments, and as long as you're not using a minus minus, then the script will be hidden and no one will see it. I still see people doing that. So if you see anybody doing that, tell them this hasn't been necessary since 1996, so knock it off. Microsoft added a language attribute because they intended to kill off JScript and replace it with their own VB script. VB script being a dialect of Visual Basic. That didn't happen. And the irony is the reason it didn't happen was because they did such a good job on JScript. If they'd done their usual thing, then JScript would not have gotten critical mass and JavaScript probably would have failed, and they had a chance to steal the market, but they didn't. So as it turned out, JavaScript was the only language that ran reliably on all browsers, and so that was the language everybody used. The only people I've seen using VB script are criminals and advertisers. Everybody else is using JavaScript. They added the source attribute, which was a really good idea, because it turns out you should not put script tags onto pages. If you put scripts into separate files, then they can be minified, they can be gzipped, they can be cached, all of which are extremely good for page startup performance, which is critical. If you put them on the page, you don't get any of those benefits. So everything should be in separate files. Then finally, W3C didn't like the language attribute because they didn't make it up. So they replaced it with their own thing. And they say that it's required. But it turns out, if you're using a source attribute, and you should, it is the server that is authoritative on what the MIME type of the asset is, not the tag that requested it. So the browsers are required to ignore it. W3C says it's required. I say leave it out. It's not necessary. It's just a waste of space. So document.write is, I hope, the worst idea Brendan Eich ever has. The way he thought that interaction with the browser was going to work was that JavaScript would run as the page is being loaded incrementally, and that JavaScript, as it's running, can insert new HTML text into the document as it's being parsed, which was kind of awful. So I don't see it being used very much anymore, except by criminals and advertisers. I see advertisers use this a lot. In the early days of web advertising, there was a huge amount of fraud. All the ad companies were ripping each other off, misreporting image views and other things. So they came up with this agreement that the way an ad placement can work is you put some ad script on your page. It will do a document.write of a script tag going to an ad server. And that one will then return code which will do a document write of a script tag going to another server. And they can do several of those things going off to different places, and it allows all of these different companies or agencies to separately count the thing so that they can all agree on what actually happened. But one of the consequences of that is they can add huge delays to the rendering of the page, because everything has to wait until all those ad redirections get finished. And it's also a huge security vulnerability, because any of those servers can be sending anything they want. And if they send something nasty, bad things happen and there's no way to defend against it. So that's all pretty awful. So I don't recommend anybody use it ever again. So unfortunately, where you put a script tag on a page can have a huge impact on the page loading time. The correct place to put script tags should be in the head, because it's meta, right? Scripts are not content, they're meta. So that's what the head is for. Unfortunately, browsers are extremely incompetent at script loading. And so if you put scripts in the head, then all parsing blocks until the scripts load, compile, and execute, which means that if there are any images in the body that need to get loaded, they don't even start to load until all the scripts have finished. And that's not good. So Steve Souders figured out that we need to move all of the scripts to the bottom of the body instead, which is great for performance but terrible for reliability, but that's what we do now. He also recommended that we minify and gzip the script files, which is very good advice. He also recommended that we reduce the number of script files as much as possible by concatenating them all together. And there are really good reasons to recommend that, because HTTP is incredibly incompetent at loading script files. And so the serial delays in HTML request transactions really hurt you badly there. So Souders recommended that you concatenate all of your script files together and turn them into one big file, and that way you avoid some of that HTTP overhead. Unfortunately, that leads to other problems. It completely breaks caching, because every page will have a different combinatorial set of scripts it's going to load, so the likelihood that one combined script file is going to be reused again is extremely low. It also introduces bugs, because there are certain errors that can happen which are not correctable if you put lots of files together. For example, you might have one file that's written by an incompetent idiot who depends on semicolon insertion, and that gets concatenated onto someone else's file, and the place where the semicolon would be inserted is no longer a insertion site because of the concatenation, and now the file fails. I talked about parsing and making trees. So this is some HTML text. This is a tree that it expands into. And there's some interesting things to observe about this. One is, first, we've got lowercase here and uppercase here. So when the web first started, the first generation of webmasters typed their markup all in uppercase because they wanted it to stand out. They wanted to make it really obvious what was markup and what was content. And writing it all in uppercase made that clearer. After a few years of that, they got tired of leaning on the shift key and they decided, oh, what the hell, and it's all lowercase now. That transition happened just as Brendan was designing the DOM. And so the DOM had to pick a convention, and the convention was, let's go with uppercase, because that's what people were using at the time. So everything that's lowercase here gets shifted up to uppercase there. And you need to be aware of that, because sometimes it doesn't matter, but sometimes it does matter. So you need to be aware. Then there are features in the tree that are not in the text. For example, I did not specify a head tag, but there is a head tag in the tree. So it'll add extra bits to the markup. Another place it'll do that is in a table. If you don't specify a t-body, it'll stick a t-body in there for you. And that can get you into trouble if you're trying to parse around things, and you'll find levels of content that you didn't expect to find. Then the other thing here is that this is the ideal Microsoft tree. So Microsoft IE6 would make a tree like this one. W3C, under the influence of the SGML community, said, no, you need to have more stuff than that. For example, the white space between here and here, which you would ordinarily ignore, that has to go into the tree. Microsoft correctly decided, no, we shouldn't do that because that's just a waste of space. But everybody else did, and now Microsoft did. Everybody does that. But I went with Microsoft tree because the real tree is too hairy and it's hard to talk about, so I'm going with the simpler tree instead. Then there's some implied hierarchy in this. For example, you've got H1, H2, and it kind of looks like the H2 is subordinate to H1, and the P's are subordinate to that, but they're not. They're all at the same level in the tree. So you need to be aware of that. Then on the JavaScript side, in the browser, there's a global variable called document, which is the root of the tree. And document.body is a shortcut for getting to the body node. There's also a shortcut for getting to the HTML node, which is called document element, which is, you would think it'd be called HTML, right? Because it goes to that one. And the reason it isn't is because at the time that document element was created, W3C was planning to kill HTML, and they didn't want to leave that evidence in the DOM. So they went with a longer name so that no one would know. But that plot didn't work. So this is a subset of the same tree. I turned it sideways to demonstrate the next thing. So each node has pointers to other nodes. For example, each node has a first child and a last child node, which point to the children. These are the neglected middle children. They don't get pointers. Then each of this P node only has one child, so both pointers point to the same element. Then there are sibling pointers. Next sibling and previous sibling, going back that way, the body will have a sibling relationship with the head tag. These guys are cousins, and you'll be glad to know there are no cousin pointers. Then there is the parent node pointer, which goes up. The body will have a parent node going to HTML. HTML will go up to the document root. And you might be going, Lordy, that's a lot of pointers. So if I edit this tree, do I have to update all those pointers? That could be kind of hairy. And the answer is no, that in fact you cannot edit the tree. These are all read-only from your perspective. You have to use the DOM API if you want to edit this tree. And I'll show you that API in a moment. Now, if it turns out all you want to do is traverse the tree, for example, if you want to visit every node in display order, you don't need all these pointers, right? If you understand how recursion works, you only need a binary tree, right? You can make that with 2 pointers. So I can use first child and next sibling with a walk the DOM function. It's a recursive function which knows how to do that traversal. And that allows me to do things like implement get elements by name by passing in a function which will look for names and compile things into a list. In addition to all of those pointers, each node also has a list of child nodes, which is kind of like an array which will have all of the children in it. You can get a node by retrieving. The way I prefer to do it is get document.getElement by ID. You can also get things by name, by tag name. You can do CSS queries and things like that. There's quite a lot of ways of getting access to a node now. Once you have access to a node, you can manipulate it. So these are the standard properties of an image tag. And if you have access to an image tag, you can change any of these properties. The most interesting one to change is the source. If you replace the source with a different URL, then suddenly a different picture will show up. And JavaScript provides a very convenient way of doing that. You just say node.property_name equals whatever value you want it to have, and it works. These are the standard properties of an image tag. Every browser will have additional properties that are unique to that browser. I recommend stay away from that stuff because it's a trap. You want to stay to the common part so you'll work everywhere. W3C was not happy about JavaScript surviving in the web after they'd rejected it. They thought that was going to be the end of it, but it didn't. And there was a lot more sympathy for Java at W3C than for JavaScript. And so over the years, they've been trying to replace the API with something that would be more friendly for Java than for JavaScript, even though Java has never lived in browsers in this way. So they didn't like the old school way of doing things, so they added this one where you can call get attribute and set attribute. This form having the obvious advantage that it's a lot more typing, and people like that. Another thing you can do when you've got hold of a node is style it. So you've got lots of options for styling. One is you can get at its class name, which is a misnamed thing. It should be .class, but it's not. It's called class name. Even though it can be several class names, it's still class name. More interesting is you can get at the style object and change attributes of the style. Microsoft added a really nice thing called current style, that sometimes you want to know what is the current attribute for something. You know, I want to know how big something is, or where it is, or what color it is currently, something like that. And Microsoft provides a very nice way of finding that out. But W3C said, nah, that's not the way we want to go. Instead, we'd rather have you write document.defaultView.getComputedStyle node get property value style name, right? This is obviously a Java API, right? I mean, nobody who knows JavaScript would write that. You know, this is clearly designed by somebody who did not know anything about JavaScript. And I don't know what happens with people in the Java world that they want to write stuff like this, but that's kind of the way things happen. So I need to rant for a moment. So CSS and the DOM were both designed about the same time. And each project was aware of the other. The guy who designed CSS was aware that someday programming languages were going to manipulate style sheets. That was a certainty. And yet, he chose to use the minus sign as a hyphen, knowing that most of our programming languages want to do subtraction with it, and that this creates a syntactic difficulty for all of you. He did that anyway. Meanwhile, at Netscape, they're working on the DOM, and they see what just happened to CSS. And they go, okay, what are we going to do about that? What they could have said was, Well, that's annoying, but we'll just say you take the brackets and you put the string in, and that's that. So you have to type 4 extra characters, but it's completely compatible. Or they could have said, well, minus signs are a problem, so we'll just change them to underbars. So, minimal change, search and replace, config. No. They went with the least compatible way of writing these names. And it matters, because you need to be aware of which space am I in right now. Am I in CSS space or am I in DOM space? And it's really easy to get confused about where you are. And if you pick the wrong form, it's total failure. They could have made this work like a system. They could have made this work well for you. And they chose not to, and it's still there, and it's never going to get fixed. Anyway, so another thing you can do with nodes is you can make nodes. You can make brand new nodes. So you can call document.createElement, pass in a tag name like a div or something, and you get a new element. That new element is not visible yet, and it won't be visible until you paste it into the tree. We'll do that next. You can make text nodes the same way. You pass a string to create text node, and it'll make you a text node, which you can then attach to some other node. Another way you can make nodes is by cloning nodes that you already have. A clone is not a perfect copy. For example, a node might have event handlers on it, but a cloned node will not. But otherwise, it's pretty similar. And if you pass true to clone node, then if the node has children, you'll get clones of the children as well. So if you want to make it visible, you have to stick it into the tree. So you can call a node and say append child the new node, and so the new node becomes the new last child of that node. And you can also insert things before, and you can replace a node with a different node. And again, this is a Java API, right? Because you have to say old twice. I could just say node, replace yourself with this. No, you have to tell the node's parent, replace that child with that one. And the way you find the parent is with the node itself. Why do you have to write old twice? Why did Java people do that? Can anyone? Anyway, you have to remove children. And so you can call node.removeChild. But again, you don't tell the node to remove itself. You have to tell the parent to remove it, so you have to do it twice. There's a particular hazard here for garbage collection if you're on one of the older IE browsers. So anybody supporting IE 6, 7, 8? Oh, you're breaking my heart. Really?
Legacy.
Oh.
Yeah.
Okay, so I was hoping I wouldn't have to say this anymore, but I do. So there is a design error in IE that if you attach an event handler to a node, that node will not get garbage collected. And the event handler and everything that it's holding onto will not get garbage collected, even if you remove that node from the tree. So the requirement is that you have to remove all of the event handlers from a node before you remove the node from the tree, which is too much to ask of anybody, but that's what you have to do. It was identified in IE 6. It was supposed to be fixed in IE 7. It wasn't. It was supposed to be fixed in IE 8, and it wasn't. I believe it finally did get fixed in IE 9. So sometimes what you want to do is take a fragment of HTML text and incorporate that into the document somehow. And W3C in their API provided no good way to do that. Their model was you would write an XML parser in JavaScript and have it parse the text, and then you would call all the methods that I just showed you and have it build the structure. Microsoft said, no, that's way too much work. So they came up with a property of a node called inner HTML, which is a terrible name, but it works. So what you do is you assign an HTML text fragment to that, and it will parse it and turn it into a tree and stick it into the document, do all of that. Very nice. Unfortunately, it's a security hazard. Anytime you have any manipulation of HTML text, particularly by concatenation, but also by templating, there's a good chance that an attacker can exploit that. So you need to be really, really cautious with this stuff. So which way is better? Is it better to build or clone elements and append them to the document, or is it better to compile an HTML text and use inner HTML to realize it? Generally, these sorts of questions I want to answer in terms of what gives you cleaner code and better maintenance, what best matches the way you make the application, that you should only favor performance in cases where it really matters. And in the cases where it really matters, you want to use inner HTML. Because one of the few things that browsers are really good at is parsing HTML. And they can do that really quickly, and they can get the whole thing done in one transaction. Whereas messing with the DOM, every time you touch the DOM, you're going to pay a big time penalty. In Netscape 2, we added an event model, which is still in all the browsers. The browser has an event-driven, single-threaded programming model, which is one of the best things about the browser. Every event will be targeted at a particular node, and the events cause the invocation of event handler functions. Unfortunately, the composition of events is really sloppy. From my perspective, there's layer confusion. There are some events which are intended for widgets, low-level components, and some intended for applications, higher-level components, and the design of the DOM mixes them all up. So you've got application-level things like click and double-click completely mixed up with widget-level things like mouse down and mouse move. Now, it turns out the silver lining here is because everything was exposed to everybody, it was possible for the libraries to come in and clean things up and impose order on it. And that worked because everything was available. But it would have been much better had they not even been necessary, if the DOM had just been designed correctly in the first place. There's similar layer confusion in the input events. You've got application level things like blur, change in focus, and key press, and widget level things like key up and key down. And again, it's all mixed up. And because it's all mixed up, I see applications mix it up. That you'll see people doing all of those things all the time, everywhere, because it's available. So there are three ways of adding an event handler to a node. There's the original Microsoft model where you could say node.onClick, assign a function to it, done. And that still works everywhere. That's pretty nice. Microsoft decided that it should be a method. So you say node.attachMethod onClick function. OK. WC said, that's not enough typing. So let's make it add event listener type F false. And this false thing is kind of weird. Normally, if you leave a parameter off, the browser will replace it with undefined, which is falsy. But in this case, it really has to be false or it's going to fail. And in a minute, I'll explain how the false is used. So an event handler takes an optional event parameter, which is how the event knows what happened. Microsoft, unfortunately, didn't do that. Instead, they had a global event variable, which was a bad thing. So because of that, this is the standard template for writing event handlers, where you either use the event that was passed in or you use the global variable. And the target is either going to be the event's target variable or property or the event's source element. Why are the two names? It doesn't make any sense. And then after that, you can do your normal thing. Now, I don't recommend that anybody use any of what I've just shown you. You don't want to use any of that because it's painful and it just doesn't work very well. You want to be using libraries instead. So there were two models for how to do event propagation. There's the trickling model that was done at Netscape, and there is the bubbling model that was done at Microsoft. So with trickling, you would start with the top of the tree, and you would descend down to the tree until you get to the target node. And any node along the way down can capture the event and say, I'm taking care of it, don't pass it down. Microsoft, on the other hand, started with the bottom, and they go up parent, 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 parent until they get to the top. And any node along the way can say, I'm interested in this event, I want to handle it. And it turns out Microsoft got it right. That bubbling up is the correct way to do that. So when W3C went to standardize, say, well, we need to come up with a standard for how we do the event propagation. Do we do the trickling down or the bubbling up? They could have said, let's do the one that's right. No, why would they do that, right? So what they instead was, we'll do it both ways. We'll require that the browsers trickle down and bubble up. So they do both. They'll first do a trickle down phase, and then they'll do a bubble up phase. And that false that was on add event listener tells you on which phase you're doing it. False will be on the bubble up phase. So why do you even care? Why do they have this bubbling stuff at all? It was to solve a problem that's probably not a problem anymore. So suppose you're making a catalog page, and you've got 100 things, and you can drag any of those things from a reservoir and put them onto a page. And so that's how you've got this nice authoring package that you're writing. And so you've got 100 draggable elements. That means you need to add a set of event handlers to each one of those. You have to add mouse down, mouse up, mouse move, and so on. So that's hundreds of sets of event handlers. In 1995, that took a long time. Browsers were a lot slower then. JavaScript was a lot slower then. It would take time to do all of that work. So instead, what you would do is add one set of event handlers to the common parent of that 100. And that common parent would intercept all of the events and move all the children as needed. I don't think it matters anymore. The systems have gotten so much faster that it's in the noise, but it's still in the model, so you still need to be aware of it. One thing you have to do is cancel bubbling. So at some point, some node has taken care of everything, and it says, please don't tell my parents, it's under control. And there are two ways to do that, and you need to be able to do it both ways. And then sometimes you want to prevent the default action. After everything is done, then the browser itself may want to do something. It may want to submit a form or give focus to something. If you don't want that to happen, you prevent that. And there are three ways to prevent that from happening, and you have to do all of those as well. Performance is a huge problem in working with the DOM. Every time you touch a node, you pay a huge time penalty. Restyling has a big cost. Reflowing has a big cost. Repainting has a big cost. Random things like node lists can have a huge cost. A node list looks like an array, except every time you touch it, it can repeat the query that caused it to come into existence, which can be wildly expensive. And it turns out in most applications, JavaScript has a very small cost. So if you took all the time that's being spent in the browser and say, this much is parsing, this much is marshalling, this much is rendering, and so on, JavaScript will be like that much. But I see people going after their code trying to shrink it down more and more and more when it's all this other stuff that's taking the time, trying to optimize that. If JavaScript engines were infinitely fast, most web applications would run about the same speed. No one would notice any difference. So you can't optimize for performance unless you have good tools. Unfortunately, we now have some good tools. For example, there's Speed Tracer on Chrome. It records micro events as your application is running on the browser. And when it's done, you can then do a post-mortem analysis, and it'll show you all the hotspots in the code and what is consuming time. And with that information, it is possible to then optimize the application. Microsoft has a similar thing called Performance Dashboard, which I think starts becoming available on IE 11. Optimization without good performance data is a waste of time. So it turns out that a small amount of JavaScript can transform the DOM, which is one of the world's awfulest APIs, into something pleasant and productive. So Ajax libraries are fun and easy to make, which is why there's so many of them, and you absolutely should be using one. They provide portability because the browsers are hugely inconsistent, and so you need a library that will deal with those inconsistencies for you, so you can be working with a much better model. They provide correction of errors that are in the specification of the DOM. They provide a much higher programming model, something where you can be much more productive. And they also provide sets of widgets, which can simplify your development work. So how do you choose? There are so many libraries out there. It would take longer to do a complete evaluation of all the existing libraries than to build a new one from scratch. I don't recommend that anybody build a new one from scratch. So some years ago, the Ajaxians suggested just throw Dart, because just picking one at random, they're all pretty good. And they're all much better than talking to the DOM directly, so you can't lose. Just pick one at random. The problem with that is that each one is a trap, that they are all extremely incompatible with each other. In fact, some are incompatible with themselves from one version to another, that point 1 of something might be completely incompatible with point 2 of something. And once you get into one of these things, you are stuck. You know, it's made of tar, and everything you write is going to be dependent on this thing, and getting loose from it and onto something else is extremely expensive and painful. So how do you decide what to do? Some years ago, I predicted that the market could not tolerate having so many of these libraries around, that there's going to have to be a shakeout. And I predicted that they would all disappear. There'd be maybe 2 winners. One of them was probably going to be Microsoft, because one of the winners is always Microsoft, and one would be something else, YUI or Dojo or jQuery or something. That turned out to be completely wrong. The number of libraries has only increased since then, and the first library to fail and completely leave the market was Microsoft's Atlas, which was so bad even they couldn't use it, and they switched to jQuery. So how do you decide? It's a really hard problem, and I do not have a solution. And we find more libraries coming online all the time, more platforms, more ways of doing stuff. And I found I can't keep up with this stuff. So how do you choose? I have no good advice except this, for what it's worth. Ask JSLint. Take any candidates that you're considering, run them through JSLint. That's an objective measure of code quality. They'll give you some indication of how well the thing's written. Maybe that's meaningful to you. Finally, one more thing about living in the browser is the problem of division and labor. Because we're now doing client-server programming. And for some people working in the browser, this is the first time to be doing client-server programming. And that means you're writing distributed application, where half of the application is running in one machine and half of the application is running in another machine. How do you divide the work? How do you decide what goes in which machine? And I've seen people make mistakes in every possible dimension. For example, early on in the web, everything was in the server. The browser was treated as a terminal, specifically as an IBM 3270 terminal, and you would send information to the server, and the server would generate a new view and send it out. And that was hugely inefficient, and it was recognition of that inefficiency which got the Ajax thing so popular. So when Ajax started, it went the other way. People started putting the entire application in the browser, and they were treating the server as a file system. And I saw people trying to basically replicate their database in the browser. They'd say, take everything we got, because who knows if we need it or not, and they'd send everything over. And then they'd complain, why does it take so long to send all that data? That turns out not to be a good way to do it either. So what's the right way? It's to seek the middle way, that you want to create a pleasant dialogue between specialized peers. You want to minimize the volume of traffic. You want to be sending stuff on a just-in-time basis. You don't need to send the browser everything it might ever need to know. You just need to send it what it needs next. And that's usually a much smaller set of data, something you can send very, very quickly, particularly as our networks have gotten so performant. And that's the end of the browser. Any questions about that? Yeah.
I'm just curious what your thoughts are on kind of the virtual DOM approach, like diffing, and I don't know if you have any opinions or.
Oh yeah, I got opinions. I don't know if they're useful opinions. So generally, the DOM is a horrible model, and propagating that horribleness onto the other side of the network, I think, just keeps you stuck in that awful model for longer. I'm hoping someday we figure out a way to liberate ourselves from the DOM, because it really is dreadful. And the thing that's encouraging to me about the libraries is that they provide a way of doing that. For example, jQuery is so much superior as an API for addressing graphical elements on a page to what the DOM provides. I would like to see us get better in that dimension.
Isn't jQuery just a wrapper around the DOM?
It is.
Okay.
But it turns out you don't need much wrappage to make the DOM significantly better. The DOM is so horrible, I recommend don't use anything that I've showed you in the last hour. Don't use
Don't use
anything.
KLM by IT ever. Just use jQuery.
Find some library. I'm not recommending jQuery
Okay.
necessarily, but some library. Every library is better than the DOM. I'm happy to say that. Even, I don't know what the worst library out there is, but whatever it is, it can't be half as bad as the DOM is.
How can, but if jQuery just calls getElement by ID, how can using a jQuery CSS selector be better than getElement by ID?
It's hiding that stuff for you. It's adding a level of abstraction. It's adding enough indirection so you're not thinking in terms of what the DOM does. You're thinking more in terms of what you need to do.
Okay.
And it's very effective at that. Lots of other libraries are too.
Okay, so other question. I kind of thought that the DOM was the browser. How'd the browser work without a DOM? Because you said there was HTML, and then right around the same time that HTML was going from all caps to lowercase, the DOM was invented. How would you have a browser without a DOM?
Before there was JavaScript, there was no need for a DOM, right?
Oh, there was no modeling of the DOM, but the DOM existed in some...
Well, the browser had a tree, but it had no API for the
Okay.
world to get access to that tree.
Okay, all right.
Yes.
I guess listening to just the history of everything, and this might be an odd question, but everything is funneled into what it is right now, and it seems like things are pretty stably moving in a very succinct way. And then when I listen to your stories of like how this came from this, and this came from this, and all of these languages came from all these other languages, do you have like an opinion or an answer to why such a minute, like how come everything is just as focused so much? Like how come there isn't so much of this development of these different ideas? Like just like when you were saying like the idea of like having returning a function took years to figure that out. Like why? Like is that still going on? And like what's going on with that? Why the slowdown?
It has always been slow. We'll talk about this on the third day. We think of ourselves as being the most innovative of industries, and maybe we are, but we're also humans, and humans tend to be extremely change-averse. And the people who are the last to recognize the value of a new technology are often the people who would most benefit from it. And there are lots of examples of that in software technology, and we'll look at those. ECMAScript 5, the new parts. So complete implementations of the 5th edition are now in all the best web browsers, and also in IE10. So it's almost everywhere. So again, to review the history of the standards, the 3rd edition was ratified in December of 1999. Work on the 4th edition started almost a year before that. The 4th edition was attempting to solve some problems that I think were unnecessary, and eventually it got so big and so complicated that it was not completable. That project slipped a year per year for 10 years. So it was eventually abandoned, and instead we did the 5th edition, which started with the working title ES 3.1, indicating that it was going to be a much less ambitious attempt at adding goodness to the 3rd edition. And it adds 2 languages, or describes 2 languages, the default language and the strict language. And of the 2, I recommend not using the default language, but using the strict language exclusively. And we'll talk later about what's in the strict language. So the goal of the ECMAScript 5 project was to make a better JavaScript. There were a lot of people who wanted us to not make a better JavaScript, but to make a different language. And there are certainly good arguments for doing that, but I think standardization is not the correct place to try to do that. So instead of trying to do a big thing, we tried to do a lot of little things. We tried to make the standard conform better to reality. There are some cases where the standard said implementations must do this, and none of the implementations did that. So we said, okay, well, the standard's obviously wrong. We should make the standard conform to what people actually do. We should try to make the browsers conform better to each other. There were cases where 3 browser makers would do things one way and Microsoft would do things another way. Microsoft very generously agreed to do what everybody else was doing. That was a very nice thing. In cases where all of the browsers disagreed, where every browser did something different, we took that as license to fix something deep in the standard. That we assume that the web doesn't care if every browser does something different. And in that case, we can go in and do deeper changes. As a result of all of this work, interoperability is improved. JavaScript was already very good at write once, run everywhere. With ES5, it gets even better. So our number one goal for ES5 was don't break the web. And that's a really difficult goal to keep because anytime you change anything, something will break. And we did break some stuff with ES5, but we tried really hard not to. Now, you could argue, as I did, there's a lot of stuff out there which deserves to break. But we tried not to break even that stuff. We wanted to improve the language for the users of the language. Most of the critics of JavaScript are people who do not use the language and would not use it even if we did everything they told us to. So we tried not to listen to them too much, not always successfully. We tried instead to listen to you. We paid a lot of attention to third-party security or mashups. We wanted to make it possible for you to add someone else's code to your page and have it not violate your security or your customer's security. We decided not to try to protect stupid people from themselves because that is just too hard. So we in fact added new ways that stupid people can do outrageously stupid things, and we'll get to that a little bit later. And we decided to have no new syntax. And the reason for that is that at the time that we were doing this work, IE6 was still the dominant browser. And our concern was that if we launched a new version of the language, and if IE6 is still dominant, then if the value of that new language depended on its syntax, then it's going to fail. Because every new feature means total failure, and that's not helping you at all. So we tried to add as much value to the language as we could without changing the syntax of the language, hoping that eventually we would solve the IE problem, and then later editions of the language would be able to be freer with syntax. So saying that, we couldn't resist adding some new syntax. So we did it, not too much, and I'll warn you, all of these are fatal errors in browsers before IE9. So if you're still in IE8, please ignore the following. So we added trailing commas in array literals, or to object literals, which is not useful. I don't recommend you use it. The reason we did that was because we fixed the way trailing commas worked in array literals. It turns out arrays always allowed that dangling comma, but they disagreed on what it meant. So in some browsers, that array would have a length of 2. On IE browsers, it had a length of 3. When you have that kind of disparity, bugs can happen. So we changed it. So the rule is now the dangling comma is ignored. So everybody will agree that it has a length of 2. We fixed a terrible reserved word policy. JavaScript's original reserved word policy said that you could not have a reserved word in name position in an object literal or in dot position. And there's no reason for that. So we fixed that. So everything that's yellow now used to be an error. That's all now OK. So that's good. In fact, the reason that JSON requires quotes around its names was because of this design problem in ES3. We added getters and setters. These are accessor properties, so that when you go to retrieve a value from an object or go to store a value into an object, instead a function will be called, which will either consume your value or return a value. And that allows some new forms of programming. So here we've got a temperature constructor, which has a Celsius property and a Fahrenheit property. You can read either one, and you can set either one. So you don't know how it works, but it just works. And that's a pretty nifty thing. Now, it turns out you can do some really stupid stuff with this, because if you use this correctly, then these methods will be very limited, very restricted in what they do. But there's no actual restriction on them. They can do anything. They can change everything in the world. And so you can, simply by reading a property of an object, you can cause things to happen over there. I don't recommend you do that because it's stupid. I'm sure somebody's going to do that. And I'll bet nobody thought that you could do that. And they'll go and do that. We actually did think about that, just hoping nobody does that. Earlier we talked about the multi-line string literals. I still think this was a mistake. Oh, this is great. So it used to be infinity, nan, and undefined were not constants. They were global variables, which meant you could change them. You could say, today infinity is 5. Let's see what happens. I know that security experts were very worried about someone redefining undefined and what the consequences of that could be. I'm not aware of any exploits that actually happened as a result of that, but it is something that was worried about. So they are now read-only variables. So that's fixed. We fixed parse int so it no longer defaults to octal when the first character is 0. I still recommend putting in the regex argument anyway, but at least the default behavior is not nearly as bad as it had been. Regular expression literals now will produce a new regular expression object every time they're evaluated, so they work the same way that functions do. The reason we did that, originally the compiler would only create one regular expression object for each regular expression literal. And the problem with that is that they contain state. For example, they contain a last, what is it, last position or last, anybody remember? The thing that exec uses to remember where the last match happened. No one knows. Anyway, there's this variable that's in there which, if everybody is sharing it, then you can't have multiple execs happening because they'll interfere with each other. So we fixed that. Oh, this was awful. So I told you earlier about the object function. It gets called every time you make an object, and the array function gets called every time you make an array. It turns out you could replace those functions with your functions, so you get called every time someone makes an object or an array. And that's a huge security violation, right? You don't want some code to be able to take those things over. So the specification will now say, as if by the original object function or array function, that you can still replace them, but you don't get the security hazard. I'm happy to report that JSON, the world's best loved data interchange format, is now built into the language. So we've got a JSON object that provides a parse function and a stringify function. Those names are my fault, completely my fault. I probably should have said encode or decode or something like that, but I didn't. So when we're stuck with those, so you're welcome. If you're using JSON2.js, then it works exactly the same, except JSON2.js knows to get out of the way if the built-in one is there, so it'll just get faster, which is what you want. We added a lot of new methods because new methods allow us to provide new functionality without new syntax, and so that's where most of the attention went. We added function.bind, which was something that jQuery has been promoting. It allows you to turn a method into a function so that you can use it as a callback. We added string.trim. So we now have a method which will remove the extraneous white space from a string. This should have been in the language from day one, right? And it shouldn't have taken this long to get that. We've got...
Does it trim on both sides?
It trims both sides.
Okay.
We didn't find enough demand to do the individuals, the left and right versions. And I haven't heard anybody complain about it. If anybody does, maybe it could get into ES7.
Okay.
Yeah.
So you just showed some JS for trim, and now is that what it's doing under the hood? It's actually just more JS, or is it written at a lower level?
It depends on the implementation.
Okay.
It could be written in a lower level. So this is called polyfilling. It's also been called monkey patching. It allows you to insert code into the system. So when Brendan originally designed the language, he only had 10 days to do this prototype. He was told that, or he expected that if his demo didn't work, that Netscape would have done something much stupider. I don't know what it would have been. I can't imagine what that would have been, but that was his race, so he only had 10 days. And he was pretty confident that he wasn't going to get everything right in 10 days, that there were probably going to need to be some tweaks in the field. So he left almost everything exposed and unlocked. So things which in a properly designed language would be locked down are completely open. So you can add things to object.prototype, for example. In a real language, you shouldn't even be able to see object.prototype. All that stuff should be sealed. And he did that probably correctly because he figured he didn't get everything right, and someday people are going to need to patch the system in real time in order to make it work, which is exactly what happened. So there's all this stuff in the language which is exposed, including this. So this, if you take this code and run it on an IE6 browser or IE7 or IE8 browser, then they will work the same way as IE10 with respect to string.trim. Now, IE10 might have its own implementation of this. It might be a native implementation, so it might run faster. So this version on IE6 runs slower. I think that's great. That's exactly how it should be. We added a large new set of array methods, and I really like these methods. The design wasn't perfect, but they're good enough that we can use these. So most of these work the same way in that you'll call a method on an array and pass in a function, and that function will get called for each element of the array. And things will happen based on what method you provide. So the every method will keep doing that behavior until a function returns false. And when a function returns false, then it stops doing that. So that allows you to loop for a time and then bail out, similar to what break might be doing in a for loop. Filter will take all of the return values. If the return value is true, then the original element of the array will be copied into a new array. So that allows you to take a big array and produce a smaller array based on what happens for each element. For each is the thing that replaces a for loop. It just goes and visits every element. I like for each. Index of will do a search. So you can do a search in an array similar to the searching you can do on strings. Last of searches the array from the back end. Map is maybe the most powerful of them. It will take every return value from that function and store it into a new array. So you can do transformations and you can do selections and lots of new things using map. Reduce will take an array and reduce it down to a single value. And it'll do that by, you pass it a function, and that function gets called for pairs of values from the array. For example, if you pass the add function to reduce, you will get a total function. If you pass a multiply function to reduce, you'll get a product function. Then there is reduce right, which reduces from the other end of the array. I've not found any reason for that. I don't know why we did that, but it's in there. Sum is similar to every, except it uses the opposite Boolean value. We added date.now. So it used to be, if you wanted to get the real-time clock, you'd have to do what this is doing. You would make a new date object with the default configuration and then extract its time. So usually when you're getting the time, it's because you want to measure something, but this process of getting access to the time adds a lot of latency. And so you can now call date now directly, and it'll give you the current value of the real-time clock. Now, browsers still add a lot of latency, and operating systems also add a lot of latency, so it's not proven that this actually does a better job, but it's not so much JavaScript's fault now, so that's gotten better. When the first standard was made, Netscape and Microsoft could not agree on the language in the standard for describing how date parsing works. There's a date constructor that can take a string, and it can then attempt to turn that string into a date object, but they couldn't agree on the details for how that worked. So instead, incorrectly, they agreed to disagree by leaving it completely unspecified. So there's no language in the standard that gives you a guarantee that if you pass it this form, that it will parse, which is kind of bad. Now, since then, ISO has come up with an international date format, which is pretty nice, sometimes called ISO text, or ISO dates or ISO strings, in which you have a year, then a dash, and a month, and a dash, and so on. So the date object will now produce strings in that form, and the date parsers are now guaranteed to accept that form. So we now have at least one date format which is guaranteed to be acceptable. So this is the first one we'll try. If that one fails, then they'll fall back on the underspecified proprietary ones. But at least there's one that's guaranteed to work.
Question about those two?
Yeah.
So the ISO format, the slide before this, everything was getting UTC times, whereas this one before, so if you do two ISO string, you're going to get everything based on the UTC time. If you do datetime.now, are you going to get server time? Or the time that the machine that the code is running on thinks it is?
You get a date object, which has a UTC.
Yeah, the date object has some fundamental time
Okay.
that's independent of the current time zone or situation.
Okay, all right, okay.
So you're getting that core value.
Okay, thank you.
We added array.isArray to the language. We tried to fix type of and couldn't. That there's too much in the web that was dependent on the broken behavior of type of. So instead we added this horrendously ugly thing, but at least we got it into the language. And Brendan actually counted the keystrokes, and this is smaller than the type of form. So even though it looks a lot worse, it's actually a little bit smaller. I managed to add object.keys, which will give you an enumeration of all of the own properties of an object. So you don't get the inherited method names, you only get the data members, which are the thing that you're probably most concerned with. And it returns it in the form of an array, which means you can then do for each on it, and so that's pretty nice.
You proposed that?
Yeah, I proposed that.
Cool. I use that all the time,
Oh.
and then I do like .length just to see like how big this object is and stuff like that.
You're welcome.
And,
Yeah, sweet.
and you were talking about earlier there's some. Was it SOME?
Yep.
How is that different than keys? Keys is an array.
Sum is for looping on an array.
Okay.
It's the opposite of every.
Every gives you all the values, some gives you all the
Every
keys.
gives you everything as long as the functions are returning true. And sum keeps working as long as everything is returning false.
Oh, but it's operating on the values, not the keys. Okay.
On the return values that are based on the function
Got
that
it.
is processing the keys.
Got it.
Yes.
Back on the dates there's a question about, are there any plans for immutable date objects?
Immutable date objects?
Yeah, I don't know what he means by that.
We're going to get to freeze. You can freeze any date object. Is that what he wants?
We don't know. I'm just gonna ask for clarification, but I'll just go on.
Okay. I also managed to get object.create added. Object.create is the primitive which makes a new object that inherits from another object. In a prototypal language, this should have been in the language from day one. So instead we had the weird thing with new and .prototype . So this gives us a direct way of doing prototypal inheritance, which is good. Then we added a meta object API to give us more control over the attributes of the properties of objects, so we can get much finer control over what's going on. So we now have two types of properties. We have data properties, which are the things we've always had, where it's just some data that you can store in the object and retrieve. And we have accessor properties. I showed you an example earlier with the temperature. object, where we can have accessors. And that's there actually have always been accessor properties in the language, but they were never exposed to you, so you couldn't make them. So there are things in the DOM like .innerHTML is an accessor property. That's why you can assign something to it and then something happens. And so there was a lot of interest in allowing you to write stuff which is as crappy as the DOM. And we succeeded. So there's no limit on the crap you can write now. So we've got objects. Objects are composed of properties. Each property is composed of attributes. Every property has 4 attributes. If you're a data property, your attributes are value, writable, enumerable, and configurable. If you're an accessor property, your attributes are enumerable, configurable, get, and set. So value is the actual value of the property. Writable is a Boolean that determines if you can read it or write it, or if you can write it. So if writable is false, it's read-only. Turns out the language has always had read-only properties, but it was never exposed to you, so you couldn't create them. Only the language could create them. So now anybody can. Enumerable means it will show up in a for in loop or will show up in object.keys. If you turn that off, it means it's not going to show up in enumerations, which means you can hide it a little bit better, that it won't get dredged up all the time. Configurable means you can delete it or you can change it into an accessor property if it was a data property. Get is a function that will be called if you try to get the property, and set is a function that will be called if you try to set the property. So having that, we've got 2 versions of a statement. The first statement is the way you could create an object literal in ES3, and the second one does exactly the same thing in ES5. And you might be thinking, thank you very much for that. That's huge. So the thing is, we wanted to be able to add this functionality, but we were constrained that we couldn't add syntax. So we wanted to make it possible, but we couldn't make it nice. But at least possible is better than impossible, which is where we were. So this means that a library can now construct objects and can have control over what's going on. So an object can designate what it wants to inherit from. It doesn't have to inherit from object.prototype. It can inherit from anything or nothing. That's never been an option before. Now we can do that. And it can say this property is not writable, it's not enumerable, it's not configurable. So we can allow you to lock those things down. And once you set one of those things to false, it can never be turned back to true again. So that gives you some control that if you want to lock your object down, you can now do that. So we added a new method, object.getProperty, which allows you to take advantage of this stuff. So this shows an example of creating an accessor property without using new syntax. So this does something similar to what we did before, but it's only using method calls. And the advantage of this form is that you can put an if around this and you won't get a syntax error if you're trying to run it on a browser that doesn't have it. Whereas with the syntax form, you can't put an if around a syntax error. So if you're trying to run it on an older browser, it will simply fail. So the meta object API contains object.defineProperty, which I just showed you, object.defineProperties, which will allow you to define several of these at once, and also object.getOwnPropertyDescriptor, which will return an object which describes the attributes of a property. I should point out that this system was clearly designed by committee. You've got things like object.create, and you've got things like getOwnPropertyDescriptor. Committees do stuff like that, right? There's no consistency on how the names work. We added a couple of methods that you'll probably never get to use. GetOwnPropertyNames, getPropertyOf. We added these for the purpose of security libraries that want to run before everything else and lock down everything that Brendan intentionally left unlocked so that the environment is now safe for third-party code to run in your environment. And in order to get at everything that needed to be locked down, it needed special access ports drilled into the language so it could get at this stuff. So what those libraries are likely to do is take these, use them, then destroy them so that nobody else can use them. So having all of this stuff, it becomes possible to do things that we couldn't do before. For example, this is the replace prototype function. It makes a perfect copy of an object, except that it now inherits from a different prototype. That's something that people have been asking for years, and there is until now, there was no way to accomplish that. Now there is. So the function itself is an ugly looking function, but you can wrap that in a name, and now you can provide that in your library, and anybody can now make an object that's got a different prototype. It used to be the case that you could add a new property to any object at any time simply by assigning to it. And you can now turn that off. If you call object.preventExtensions and pass it an object, that object will now refuse to accept new properties. If you attempt to give it a new property, it'll throw an exception instead. And we can go even further than that. We can freeze the object. Freeze prevents extensions and also makes every property read-only and non-configurable, which means it is now an immutable object. And that has some nice properties. It means that future versions of the language may be able to make some interesting optimizations because they can make assumptions that this object cannot change. That means we can be smarter in the way we generate code for that object. It also means that we can take a frozen object, hand it to a third party, and be confident that the third party cannot corrupt or tamper with the object. And that's an extremely valuable thing, particularly as you know, we're doing more and more complicated stuff with more parties. We added a strict mode to the language because there are a lot of things in the language that were clearly wrong that we wanted to repair, but they would be breaking changes. And so we needed to have some kind of opt-in. So you'd say, yes, I'm prepared for the breakage this might cause because I want to be using the better language. The difficulty we had in specifying this was, how do you say, I want strict mode without introducing new syntax? Because we wanted older browsers to simply ignore the fact that we're in strict mode and work the way they always have. So we spent a lot of time trying to figure out how to do that, and eventually we came up with a terrible hack. We used the useless expression statement that I was complaining about earlier to specify the pragma. So if the first statement of a function or a file is the string use strict semicolon, that puts that file or that function into strict mode. And on older browsers, that's simply ignored and does nothing. So that works. We've got the file form, which is good if you're on Node. If you're on a browser, I recommend you only use the function form. The reason for that is Steve Souders will tell you to concatenate all of your files together, and that means that all of your files will have the same strictness as the first file. And that could be bad in any number of ways. So in browsers, we recommend you only use the function form. Strict mode adds a number of new reserved words. So far, I'm only aware of let and yield being used in the next edition of the language. The others may or may not be used in other editions. This is the list of things that are provided by strict mode. Unfortunately, it's a boring list, so I'm just going to read the boring list. There are no more implied global variables within functions. This was a huge design error in JavaScript. So now if you forget to declare a variable in a function, it's going to be a syntax error. It's not going to default to global variables. So that's good. This is no longer bound to the global object by the function form. So if you call a method as a function, this will get bound to undefined and not the global object. That turned out to be really important for security. The call and apply methods no longer default to the global object. So it used to be if you called the apply method, and passed in null or undefined, meaning you don't want this to get bound to anything, JavaScript would go, oh, you can't mean that. You probably mean the global object, and would do that substitution. It doesn't do that anymore. We got rid of the with statement. If you try to assign to something which is not writable, you will now throw an exception. It used to fail silently, which is really bad for integrity, because the code may have made a change assuming that it succeeded in making the change, and if the change failed and it isn't notified, then it could become inconsistent. We did a similar thing with deleting non-configurable properties. We put restrictions on eval. I haven't talked at all this week about eval, and I'm not going to. Eval is the most misused feature of the language, and I don't recommend using it. And the implementation of it in the old language was really quite horrible, that it gave extreme powers to whoever provided a string to it. And so we put some limits on eval. The thing I complained about with arguments getting bound strangely to the parameters, that's been fixed. We got rid of arguments.caller and arguments.callee, and getting rid of those was surprisingly difficult because arguments.caller had never been in the standard. So we couldn't simply go to a line of the standard and delete it. Instead, we had to add caller to the language and then poison it. We got rid of octoliterals because we found that they are confusing to humans. Most people in school learned that a leading 0 in front of a number is not significant, but JavaScript said it was and turned you into base 8. So we fixed that. And that got us a lot of complaints from the Node community. Apparently the Node guys are still using octoliterals for setting file permissions. I didn't know anybody was still doing that. But they are. So ES6 added octal back in, but in a slightly less awful way. And then duplicate names in an object literal or function parameters are now a syntax error. So if you say function foo a comma a, it'll now recognize that the second a is an error. We fixed the new operator. So forgetting to use the new prefix in strict mode will now throw an exception and not silently clobber global variables. So that's good. There are a few things that we know did break because of strict mode. For example, if you call add event listener in a browser intending to add an event to the window object, that accidentally worked in the old language. And the reason it accidentally worked was in the browser, the window object is the global object. They just happen to be the same thing. And when you call a function as a function, this gets bound to the global object, which happens to be the window object. So it worked. It was never intended to work. It just accidentally worked. So now in strict mode, you have to be explicit. If you want to add an event listener to the window, you have to say window dot. There's nothing in the language that will tell you if you are in strict mode or if strict mode is available, but you can write either of these little functions and they will tell you exactly what you need to know. The design of strict mode was informed by JSLint. They're not entirely the same because JSLint is forced to do a static analysis and strict mode can do some things dynamically, but if you're using JSLint, and you should, then you should be very happy with strict mode. A lot of the work that we did was motivated by the problems of mashups. A mashup is where you've got code representing two parties that wants to work together in the same page for the benefit of the user without one being able to corrupt the other. And that turns out to be a very difficult problem. So we don't have a complete solution to that, but we are on the road to solving that. So the design of the mashup solutions that we put into the language were derived from Google's Kaha project and my own AdSafe project. And by fixing things like the binding of this and some of the other problems, we can now get security solutions which provide all the benefits of both of these, which should be a good thing. So any questions about any of this stuff about ES5? Or anything about anything today? Or anything at all?
Just in the discussion, we're all talking about ES6 and stuff like that, but
We'll get to ES6 on the third day.
Yeah, that's what you had that in the schedule, so.
Okay, anybody else?
When you talked about how pervasive certain constructs are out in the web and figuring out how much you'd break and stuff like that, how did you gather those metrics?
Yeah, it's really hard. Some of it was just, I think somebody did something. You know, I heard about a guy who did something. You know, a lot of it was that. Some of it was mining Google code. Microsoft also had an extensive database of code, and we would mine against that. I'm not confident how effective our tools were in all cases because some of the patterns we're looking for are really complex, and some code is so badly written that you might not necessarily be able to recognize the patterns. But we tried as much as was possible given the technology available to match stuff against what the web was doing.